Please subscribe to support the channel. Throughout the universe, stars are not just twinkling points of light, they are colossal engines of energy, capable of both sustaining and destroying life. Among them are the truly extreme, stars so massive, so unstable, and so volatile that their very existence poses a threat even across the immense emptiness of space. These are not the quiet, steady stars like our Sun that burn gently for billions of years, but rather unstable cosmic titans living dangerously fast and powerful lives. They shine furiously, shedding their material in violent outbursts, and often end their existence in cataclysmic explosions that reverberate across the galaxy. Such stars are rare, but when they do exist, they become both a scientific mystery and a looming reminder of just how chaotic the universe can be. The dangers these stars present extend far beyond their own systems. A sufficiently massive star nearing the end of its life can unleash energies that dwarf anything humanity could imagine. The sheer radiation, shockwaves, and high-energy bursts they release can alter the chemistry of interstellar space, shape the evolution of galaxies, and even pose risks to planets thousands of light-years away. To put this into perspective, while most celestial events are so distant that they have no tangible effect on Earth, certain stars are capable of discharging enough power to at least be considered a potential hazard across incomprehensible distances. When astronomers look at these unstable giants, they see more than just danger. They see a laboratory for understanding the life cycle of the universe itself. Massive stars are factories of heavy elements, oxygen, carbon, iron, the very materials needed to build planets, atmospheres, and life. Yet, the way they live and die is wrapped in mystery. How do they maintain their structure despite their size? Why do some explode in a supernova while others collapse into black holes without so much as a flare? What unseen processes govern their violent outbursts? These questions drive astronomers to watch them closely, sometimes for decades, sometimes for centuries. And among these rare, unstable stars, there is one that stands out above nearly all others. A star system so powerful, so unpredictable, and so luminous that it has captured human attention for centuries. It is not just a star, it is a cosmic enigma, one of the most dangerous celestial bodies ever discovered. For scientists, for dreamers, and for anyone who contemplates our fragile place in the cosmos, this star serves as both a warning and a wonder. Its name is Eta Carinae, a star system that has been both a beacon and a terror in the night sky. For centuries, astronomers, navigators, and skywatchers alike have marveled at its brilliance and feared its unpredictable nature. Unlike many other stars, which fade quietly into obscurity or remain steadfast for millions upon millions of years, Eta Carinae has built a reputation for unpredictability, eruptive violence, and a raw display of cosmic power. To call it just another star would be like calling a raging supervolcano just another mountain. Eta Carinae is, without exaggeration, one of the most dangerous and mysterious stars ever discovered. What immediately sets Eta Carinae apart is its presence in human history. Long before the age of advanced telescopes, this object was already known as an unusually bright and changeable star. In the mid-19th century, it commanded the attention of the world by undergoing an eruption so powerful that it temporarily became the second brightest star in the night sky, outshone only by Sirius. At that time, even without modern astrophysics, observers realized they were witnessing something extraordinary, something that defied the normal behavior of stars. This act of cosmic violence would forever brand Eta Carinae as one of the most peculiar objects in our galaxy. But Eta Carinae isn't just famous for one historical event. It is infamous because it represents the very limits of what stars can become. Astronomers classify stars by their size, luminosity, and life cycle, and Eta Carinae falls into the category of luminous blue variables, a class of star that is as rare as it is unstable. These stars are known to be short-lived, prone to sudden outbursts, and teeter constantly on the brink of self-destruction. Within this already extreme class, Eta Carinae sits at the very top of the danger scale, embodying instability, power, and mystery like few others. The danger comes not just from its size but from the fact that it is nearing the end of its life. Astronomically speaking, massive stars are like fireworks. They burn fast, they burn hot, and they end dramatically. Eta Carinae has already shown us a preview of its volatility with its 19th century eruption, and scientists believe that this was only a precursor to its inevitable final act, a massive supernova or perhaps even a hypernova. To put it simply, Eta Carinae is a ticking time bomb in the cosmos. One of the reasons astronomers remain so fascinated with Eta Carinae is because, despite centuries of observation, it still refuses to fit neatly into any established model of stellar behavior. Most stars, no matter how massive, follow relatively predictable patterns. They expand, they contract, they shed mass in measurable ways. Eta Carinae, however, has written its own rulebook. It brightens dramatically, then fades, then stabilizes, then flares again. It creates huge nebulae of ejected gas and dust, only to remain intact when most stars would have already blown themselves apart. It emits powerful winds and radiation that interact in violent, unpredictable ways, baffling scientists who try to simulate its behavior. It is no exaggeration to say that Eta Carinae has been called the most dangerous star in the Milky Way galaxy. While there may be other candidates for this title, few stars combine its proximity, size, instability, and potential for destruction quite so dramatically. Its reputation is so profound that some astronomers describe it as a cosmic monster, one whose true destructive potential has not yet been realized but could, at any moment in cosmic time, reveal itself in spectacular and terrifying fashion. And yet, alongside the danger lies beauty. Eta Carinae is not simply a threat, it is also a wonder. It represents the extremes of nature, a natural laboratory for studying phenomena that cannot be recreated on Earth. In its instability, astronomers see opportunity, a chance to understand how stars shed mass, how they evolve in their final stages, and how they interact with their environments. For humanity, it is both a looming storm and a cosmic jewel, blazing fiercely in the constellation of Carina. The name Eta Carinae itself is tied to its location within the sky. The Eta designation comes from the system astronomers use to catalogue stars within constellations, and Carinae places it within the Carina constellation, Latin for the keel, a reference to the keel of a ship. And in a sense, this is fitting. Eta Carinae has become the flagship of unstable stars, guiding astronomers through the turbulent waters of stellar physics, sometimes illuminating, sometimes confounding, but always commanding respect. When we speak of Eta Carinae, we are not merely describing a star system. We are speaking about a cosmic riddle, one that has haunted human curiosity for nearly 2 centuries and continues to challenge our understanding of the universe. It is dangerous, yes, but it is also captivating, a reminder that the universe is not just a silent backdrop of twinkling lights but a living, evolving, and sometimes violent stage where forces beyond imagination are constantly at play. Eta Carinae's home in the cosmos is as remarkable as the star itself. It resides approximately 7,500 light-years away from Earth, nestled deep within the Carina constellation, one of the grand and storied regions of the southern sky. To put that distance into perspective, a single light-year equals nearly 9.5 trillion kilometers, which means Eta Carinae is over 70 quadrillion kilometers away from us. Despite this unimaginable distance, the star system is so monstrously bright and active that it still leaves a noticeable mark on our night sky, visible through modest telescopes and even faintly to the naked eye under perfect dark sky conditions. That fact alone hints at its raw power. Most stars at such a distance would be utterly invisible without sophisticated instruments, yet Eta Carinae demands attention. The constellation Carina itself carries historical and cultural weight. In Latin, Carina means the keel of a ship, and it was originally part of the much larger constellation Argo Navis, which represented the ship of Jason and the Argonauts from Greek mythology. Eventually, astronomers divided Argo Navis into 3 smaller constellations: Carina, the keel; Puppis, the stern; and Vela, the sails. Eta Carinae became the jewel of the Carina constellation, often described as its crown star, though star doesn't capture the full complexity of this binary system. The region of space Eta Carinae inhabits is more than just its constellation. It sits within one of the richest and most visually stunning parts of our Milky Way galaxy, the Carina Nebula. This vast, glowing cloud of gas and dust stretches across hundreds of light-years and serves as a stellar nursery, birthing new stars while being illuminated by the massive stars already formed within it. The Carina Nebula is one of the brightest and most active star-forming regions visible from Earth, rivaling even the famous Orion Nebula in its majesty. In this grand setting, Eta Carinae is the centerpiece, the brightest, most dangerous, and most studied resident. Astronomers often describe the Carina Nebula as a canvas painted with extremes. Within it are enormous columns of gas sculpted by stellar winds, clusters of newborn stars, and regions glowing with ionized hydrogen. And then, Dominating all of it sits Eta Carinae, whose violent history and immense luminosity shape its surroundings in profound ways. The radiation and stellar winds blasting from Eta Carinae carve out cavities in the nebula, compressing clouds of dust and gas and possibly triggering the birth of new stars. At the same time, its violent outbursts, such as the one that produced the Homunculus Nebula in the 19th century, add new materials to this cosmic environment, seeding it with elements that will later become part of other stars and planetary systems. In other words, Eta Carinae is not just a resident of Carina, it is one of the forces shaping it. For observers on Earth, finding Eta Carinae requires looking to the southern skies. Because of its position in Carina, it is not visible from much of the northern hemisphere, making it a treasure primarily for southern stargazers. From latitudes closer to the equator and into the southern hemisphere, however, Eta Carinae sits proudly within the Milky Way's brilliant band, surrounded by some of the most spectacular deep-sky objects astronomers can observe. In fact, professional and amateur astronomers alike often describe the Carina region as one of the most rewarding areas of the sky to explore. The star system's distance of 7,500 light-years also adds a fascinating dimension to the story. When we see Eta Carinae, we are looking into the past. Light takes time to travel, so the photons reaching our telescopes and eyes today left Eta Carinae about 7,500 years ago, long before the rise of human civilization as we know it. This means that the star could, in theory, have already exploded in a supernova or hypernova in real time, and we simply haven't seen it yet because the light hasn't arrived. Every time astronomers point their instruments toward this volatile star, they are essentially checking a cosmic time capsule, waiting to see if and when its final act will be revealed. Eta Carinae's location in such a rich, dense part of the galaxy also makes it particularly important for research. Being surrounded by other massive stars, dense molecular clouds, and active star-forming regions provides scientists with a laboratory to study how the most massive stars interact with their environments. In a sense, the Carina constellation is not just Eta Carinae's backdrop but part of the story of how such stars evolve and influence the galaxy around them. Finally, there is something poetic about Eta Carinae's placement. A ship's keel in mythology provides both stability and direction, yet Eta Carinae is anything but stable. It is a reminder that even within the constellations humans named for their symbols of navigation and adventure, there lurk forces beyond comprehension. Cosmic storms that could outshine entire galaxies for a brief moment in time. What makes Eta Carinae so special is not just one attribute but a convergence of extremes. Its sheer size, extraordinary brightness, and explosive history. Many stars are massive, some are bright, and others have fascinating life stories. But Eta Carinae combines all of these qualities into one chaotic package. It is the very definition of a stellar outlier, the kind of object that forces astronomers to rethink the boundaries of what stars can do and how far they can be pushed before they collapse under their own weight. First, there is its size. Eta Carinae is not just larger than the Sun, it is incomprehensibly larger. The primary star in the system is estimated to be somewhere between 100 and 150 times the mass of our Sun, and possibly even greater. That alone makes it one of the heaviest stars humanity has ever catalogued. Stars this massive are exceedingly rare because they live short lives. Their enormous gravity compresses their cores so tightly that nuclear fusion runs at a breakneck pace, burning through their fuel in only a few million years rather than billions. To even find a star at this stage is remarkable because it represents a fleeting chapter of cosmic history. But mass alone does not capture Eta Carinae's intensity. Its luminosity is equally staggering. This star system shines with a brightness estimated to be millions of times greater than the Sun's output. If Eta Carinae were placed where our Sun is today, Earth would be instantly scorched, vaporized, and obliterated, and even Pluto, billions of kilometers away, would be bathed in a searing light that would strip away any atmosphere or ices. This blinding luminosity is one of the key reasons why Eta Carinae remains visible to us across 7,500 light-years of space. Imagine the scale of that, a cosmic lantern so intense that it beams through dust, nebulae, and galactic distance to still reach our skies with measurable force. Then, of course, there is its history of eruptions. Stars of such mass are inherently unstable, but Eta Carinae has distinguished itself with its unpredictability. The most famous event occurred in the 1840s, when it underwent what astronomers call the Great Eruption. Without actually destroying itself, The star brightened so dramatically that it briefly became the second brightest star in the entire night sky, outshone only by Sirius, even though Sirius is a mere 8.6 light-years away while Eta Carinae is nearly 1,000 times farther. This eruption spewed out an estimated 10 to 20 solar masses of material into space, the equivalent of ejecting 10 suns worth of gas and dust, forming the Homunculus Nebula that still surrounds it today. The sheer violence of this event left astronomers of the time stunned, and even now, modern scientists continue to debate exactly what caused such a powerful yet incomplete explosion. The combination of size, brightness, and violent instability makes Eta Carinae a star system of contradictions. It is too massive to last long, yet it refuses to collapse. It has erupted with the force of a supernova but has not yet destroyed itself. It is so bright that it outshines most stars in its galaxy, yet it flickers unpredictably, as if undecided on how much energy it should release. For astronomers, this makes it not just special but invaluable, because every anomaly provides a clue to the mysteries of stellar evolution. Another reason Eta Carinae stands out is its potential to serve as a preview of the future. Stars like this are extremely rare, and humanity does not often get the chance to study them up close. By watching Eta Carinae, scientists get a front-row seat to the processes that govern how the most massive stars live and die. These processes are central to the evolution of galaxies because massive stars are responsible for forging and spreading the heavy elements that make planets, and life itself, possible. Thus, Eta Carinae is not just fascinating on its own, it is also critical to understanding our cosmic origins. There is also a cultural dimension to why it is special. The Great Eruption of the 19th century was one of the first times humanity collectively witnessed such a dramatic stellar outburst. Observers across the globe, using primitive telescopes by today's standards, documented the event, debated its causes, and speculated about what it meant. In many ways, Eta Carinae became a bridge between the era of naked-eye astronomy and the age of modern astrophysics. Today, with space telescopes like Hubble, Chandra, and the James Webb Space Telescope, we continue to peel back its layers, finding new mysteries in a star we have already been watching for nearly 2 centuries. When you combine its immense scale, blinding radiance, and explosive unpredictability, Eta Carinae becomes more than just another entry in a star catalogue. It becomes a symbol of the universe's extremes, a reminder that nature is capable of crafting giants so unstable that they live on the edge of destruction. It is, in every sense, a cosmic paradox, one of the brightest yet most unstable stars, one of the most violent yet still intact, one of the most observed yet still deeply mysterious. And that is why astronomers are fascinated, because Eta Carinae forces us to confront the limits of our understanding and beckons us to keep asking questions about the life and death of stars. When we talk about stars, it is often easy to lose perspective because the numbers are so enormous, the scales so far beyond human experience, that they stop feeling real. To grasp Eta Carinae's true magnitude, we must compare it with the one star we know best, our Sun. The Sun is the foundation of life on Earth, a steady yellow dwarf that burns calmly and predictably, supplying just the right amount of heat and light for billions of years. It feels impossibly large when we look at it from our small planet, a glowing disk that dominates the daytime sky. Yet in the grand hierarchy of stars, the Sun is modest, even ordinary. When placed alongside Eta Carinae, it becomes a mere flicker compared to a raging inferno. Eta Carinae's primary star alone is estimated to be 100 to 150 times more massive than the Sun. That means if you were to line up suns like marbles on a cosmic scale, you would need over 100 of them just to balance the weight of this one colossal star. And that's not even accounting for its companion star, which is itself dozens of solar masses in size. To put it into perspective, stars with even 30 solar masses are already considered enormous and rare. Eta Carinae's mass makes it one of the true titans of the galaxy. But the difference in brightness is even more astonishing. Eta Carinae radiates with a luminosity estimated to be about 5 million times greater than that of the Sun. Imagine 5 million suns shining together, their combined brilliance condensed into a single stellar system. That is what Eta Carinae pours into the cosmos every second. If Earth was somehow transported into orbit around Eta Carinae at the same distance it currently sits from the Sun, our planet would be reduced to a smoldering cinder in an instant. The oceans would boil away, the atmosphere would strip off into space, and the very rocks of Earth's crust would vaporize almost immediately. Even in terms of size and scale, the difference is staggering. The Sun's diameter is about 1.4 million kilometers, big enough that you could fit over a million Earths inside it. Yet Eta Carinae's bloated, unstable outer layers could stretch to over 200 times the Sun's radius. If placed at the center of our solar system, Eta Carinae would extend well beyond the orbit of Mars and perhaps even encroach on Jupiter's territory, swallowing up Mercury, Venus, Earth, and Mars along the way. Our entire planetary neighborhood would be engulfed by its immense bulk. Another useful way to compare is to consider energy output. The Sun generates about 386 billion megawatts of energy every second, enough to power all human civilization millions of times over. Eta Carinae, by contrast, emits more energy in 1 second than the Sun does in several years. In fact, during the Great Eruption of the 1840s, Eta Carinae temporarily outshone every star in the night sky except Sirius. And remember, Sirius is close, only 8.6 light-years away, while Eta Carinae is nearly 1,000 times farther. The fact that it could rival and even surpass Sirius despite the vast difference in distance highlights just how overpoweringly luminous it truly is. Another staggering comparison lies in its lifespan. The Sun, with its modest mass, will live for about 10 billion years in total. It has been burning for 4.6 billion years already and will shine for another 5 billion or so before swelling into a red giant and eventually settling into a quiet white dwarf. Eta Carinae, on the other hand, will not be so lucky. With its monstrous mass, it burns through its nuclear fuel at a furious pace. Astronomers estimate it may live for only a few million years in total, less than 1,000th of the Sun's lifespan. In cosmic terms, it is a flash fire compared to the Sun's steady hearth. This disparity highlights the trade-off for such massive stars. Brilliance and power come at the cost of stability and longevity. To further appreciate the scale, consider this: if our Sun was shrunk to the size of a basketball, Eta Carinae would be larger than a school gymnasium. If the Sun were represented as a single candle in a dark room, Eta Carinae would be an entire stadium filled with floodlights, searing the eyes and overwhelming everything around it. These analogies, though imperfect, hint at the profound difference between a middle-class star like the Sun and a hypergiant like Eta Carinae. This comparison is not meant to diminish the Sun, for without it, life on Earth could never have arisen. But it does place our star in perspective. The Sun is stable, dependable, and long-lived. Eta Carinae, by contrast, is violent, unstable, and fleeting. They represent two very different evolutionary paths for stars, one that nurtures life and another that obliterates everything nearby in its furious march toward destruction. Astronomers find this contrast compelling because it shows the full range of stellar possibilities. From small red dwarfs that can burn for trillions of years to massive giants like Eta Carinae that blaze out in a cosmic instant, stars come in many sizes and temperaments. Eta Carinae represents the extreme, a true upper limit of what nature can achieve. Its comparison to the Sun is a lesson in humility. What we consider vast and powerful is, in fact, modest when measured against the universe's greatest engines of energy. What makes Eta Carinae even more extraordinary is that it is not a single star at all, but rather a binary system. Two colossal stars locked in a gravitational dance so intense and volatile that their interaction itself drives much of the chaos we observe. This fact adds another layer of complexity to an already extreme cosmic object. Studying one hypergiant star would be fascinating enough, but Eta Carinae gives us two massive stars orbiting each other, each contributing to the instability, each fueling the other's fury. Astronomers were not always certain Eta Carinae was a binary. For decades, it was assumed to be just one star because its brilliance and eruptive behavior overshadowed any signs of a companion. Only with modern telescopes and careful analysis of the light, winds, and X-rays streaming from the system did scientists confirm the presence of the second star. And what they found made Eta Carinae even more intriguing. Instead of a small, insignificant partner, the companion is itself a giant, boasting tens of solar masses and immense luminosity. This is not a David and Goliath pairing, but rather two giants clashing together in a cosmic rivalry. The orbit of the two stars is highly elliptical, meaning that instead of circling each other in neat, uniform paths, they swing close together and then fly far apart in elongated loops. Their orbital period is about 5.5 years, so every 5.5 years, the stars reach their closest approach, an event astronomers watch closely because it triggers dramatic changes in their behavior. When they draw near, their stellar winds collide with maximum intensity, creating massive shockwaves, flares of X-ray radiation, and shifts in brightness that ripple through the entire system. The gravitational interplay between the two is also thought to have influenced Eta Carinae's most famous outburst, the Great Eruption of the 1840s. Some theories suggest that the companion star may have destabilized the primary star by drawing material away from its outer layers or by disturbing its balance during one of their close approaches. In this way, the binary nature of Eta Carinae might be directly tied to why it has been so explosively volatile throughout its history. To appreciate just how unusual this is, consider that most binary systems contain stars of average size. Our own nearest stellar neighbor, Alpha Centauri, is a triple-star system, but the stars there are relatively ordinary. Eta Carinae, by contrast, contains two titanic stars, one estimated to be between 100 to 150 times the mass of the Sun and the other somewhere between 30 to 80 solar masses. Either one of these stars, on its own, would be among the largest known in the galaxy. Together, in a single system, they form a pairing of extremes that is almost unmatched. The interaction between the two stars creates an environment that is anything but calm. Their combined luminosity means the system shines with more energy than nearly any other known stellar pairing. Their winds crash into one another at speeds of thousands of kilometers per second, producing shockwaves that heat gas to millions of degrees, which we detect as high-energy X-ray radiation. These violent collisions are not mere curiosities. They actively shape the surrounding nebula, sculpting the material ejected in the past and influencing what we see when we look at Eta Carinae through telescopes. The binary system also explains one of the most puzzling aspects of Eta Carinae, its periodic variability. Observers noticed long ago that its brightness and emissions seem to fluctuate on a repeating cycle. Today we understand this is tied to the orbital motion of the two stars. As they swing closer together and then farther apart, the conditions in the system change dramatically. When they approach, the colliding winds produce intense X-rays, but as they pass and move apart, the activity wanes, only to build again in a predictable cycle. This regular rhythm, superimposed on Eta Carinae's larger unpredictable behavior, makes it a particularly rich system to study. Perhaps the most fascinating part of this binary is how the companion star manages to survive in such an extreme environment. The primary is unstable, shedding mass in enormous quantities, blasting radiation, and producing stellar winds strong enough to strip smaller stars bare. Yet the companion, though battered, persists, circling faithfully every 5.5 years, feeding the chaos without succumbing to it, at least not yet. For astronomers, the binary nature of Eta Carinae is more than a curiosity. It offers a rare opportunity to study how massive stars interact. Most of the time, we can only observe solitary stars as they evolve and eventually die. With Eta Carinae, we get to witness how two giants influence each other's fates, how their gravitational pulls, their stellar winds, and their radiation combine in a volatile cosmic partnership. It's as though the universe has staged a grand performance, with two of its most powerful actors locked in a dangerous duet, and humanity has front-row seats to the show. At the heart of Eta Carinae lies the true monster of the system, the primary star, a behemoth whose very existence defies the limits of stellar stability. Estimated to be between 100 and 150 times the mass of our Sun, this star ranks among the most massive ever observed in the Milky Way. To appreciate just how rare and extreme that is, consider this: out of the billions of stars in our galaxy, only a tiny fraction are born with even 50 solar masses. Stars that push beyond 100 solar masses are almost unheard of, and those that survive long enough to be studied are rarer still. Eta Carinae's primary is a true outlier, an unstable colossus perched on the brink of destruction. The first thing that defines this star is its instability. Unlike our Sun, which burns hydrogen steadily and predictably, Eta Carinae's core is a raging furnace, fusing elements at an accelerated pace because of its enormous gravity. This furious rate of fusion means it generates outward pressure to counteract the crushing inward pull of its own mass. But here's the problem: the balance between gravity and fusion is incredibly delicate in stars of this size, and in Eta Carinae's primary, that balance is constantly teetering. This is why it experiences such violent episodes of mass loss, such as the Great Eruption of the 1840s, when it shed multiple suns' worth of material in one cataclysmic outburst. With so much mass, the star also teeters dangerously close to the Eddington limit, the theoretical maximum luminosity a star can achieve before its radiation pressure overpowers its own gravity. Essentially, The star is shining so intensely that its outward radiation is trying to blow itself apart, while gravity desperately tries to hold it together. Stars like Eta Carinae's primary live in this precarious zone, constantly shedding mass in winds and eruptions, as though trying to save themselves from total collapse. This makes them unstable by nature, bright, powerful, and spectacular, but doomed to a short, violent existence. This instability also means Eta Carinae's primary is nearing the end of its life. Stars of such enormous mass burn their nuclear fuel at astonishing speeds. Whereas the Sun has a lifespan of about 10 billion years, Eta Carinae's primary will likely only survive for a few million years total. It has already passed through much of its stable hydrogen burning phase and is thought to be burning heavier elements in its core, inching step by step toward the inevitable moment when its nuclear furnace can no longer resist gravity. When that happens, collapse will come swiftly, and the result will almost certainly be a supernova, or perhaps something even more dramatic, like a hypernova. Another defining trait of this primary star is its sheer luminosity. It shines with the power of several million suns combined, sending out light and radiation across the electromagnetic spectrum. Its glare is so intense that it ionizes the gas around it, reshaping the Carina Nebula and blasting apart clouds of dust that drift too close. This flood of radiation doesn't just affect the surrounding nebula, it also has profound effects on its companion star. The smaller star must endure a constant bombardment of radiation and stellar wind, making their orbital dance a high-stakes interaction of raw cosmic power. What makes this star even more fascinating to astronomers is that it has already demonstrated behavior more violent than most stars will ever exhibit in their entire lifespans, and yet it continues to exist. The Great Eruption was so powerful that it mimicked a supernova without actually destroying the star. Most stars would not survive such an outburst, but Eta Carinae's primary endured, though weakened, scarred, and more unstable than ever. This resilience makes it a unique case study for stellar astrophysics, a rare example of a supernova-like event that left its progenitor intact. In addition, the star's massive size and instability make it a candidate for producing one of the universe's most dangerous phenomena, a gamma-ray burst. If and when it explodes, astronomers believe there is a chance it could unleash a focused beam of high-energy radiation capable of sterilizing entire planetary systems in its path. Fortunately for Earth, current evidence suggests we are not aligned with such a potential beam. Still, the very possibility that a single star could threaten worlds thousands of light-years away is a testament to the terrifying power locked inside Eta Carinae's primary. The primary star is, in many ways, living on borrowed time. Every outburst, every fluctuation in brightness, every cycle of instability is a reminder that its clock is ticking. Astronomers watch it like a surgeon monitoring a critically ill patient, knowing that the end could come suddenly, or it could drag on for thousands more years. Each observation is not just about tracking one star but about trying to understand how the universe's most massive giants live and die, because Eta Carinae's fate will echo across its entire region of the galaxy, reshaping nebulae, seeding new stars, and leaving behind either a black hole or a neutron star as a final relic. It is hard not to feel a sense of awe when contemplating the primary star of Eta Carinae. It is both a marvel and a menace, a star that defies the odds just by continuing to exist. For scientists, it represents a living experiment in the limits of stellar physics. For humanity as a whole, it is a reminder that the universe contains forces so vast, so raw, that even across thousands of light-years they command our attention. If Eta Carinae's primary star is the towering giant at the center of this drama, then the companion star is the equally vital but often overlooked supporting actor, smaller in comparison, but still vast and powerful by any normal standard. Estimated to be somewhere between 30 and 80 times the mass of our Sun, this so-called smaller star would, in almost any other context, be considered one of the true monsters of the galaxy. In the shadow of Eta Carinae's primary, however, it becomes the quieter half of a cosmic duet, though its role is anything but passive. The companion star is thought to be an extremely hot, massive O-type star, possibly a Wolf-Rayet star or a star transitioning toward that phase. Wolf-Rayet stars are among the hottest and most luminous in the universe, known for shedding their outer layers at phenomenal rates. This fits the picture of Eta Carinae's companion, a powerful, compact, and extraordinarily energetic star that may not be as bloated as the primary, but is arguably more ferocious in the winds and radiation it unleashes. Its significance lies not just in its size or luminosity but in its relationship with the primary. Locked together in a highly elliptical orbit of about 5.5 years, the companion plays the role of both partner and provocateur. Every time it swings close to the primary, it stirs the system into chaos. Its stellar winds, blowing outward at speeds of up to 3,000 kilometers per second, slam directly into the slower but denser winds of the primary star. This violent collision creates a shock front, a kind of cosmic storm zone where temperatures soar to millions of degrees, producing intense X-ray radiation detectable even from Earth. In essence, the companion star acts like a battering ram, intensifying the turbulence of an already unstable system. These close approaches may also help explain Eta Carinae's greatest outburst, the Great Eruption of the 1840s. Some astronomers suspect that during periastron, the point of closest orbital approach, the companion's gravitational pull disturbed the primary star so severely that it triggered the cataclysmic release of 10 to 20 suns worth of material into space. In this view, the smaller star did not simply observe the eruption, it helped ignite it. Even today, many of Eta Carinae's fluctuations in brightness and energy output are tied directly to the orbital motion of the companion, which acts as a destabilizing influence on its massive neighbor. But the companion is not merely an instigator. It also plays a critical role in shaping the environment around Eta Carinae. The colliding winds carve out cavities in the surrounding gas, channeling material into vast arcs and shock zones. These structures have been imaged in exquisite detail by telescopes like Hubble and Chandra, revealing how the companion's fierce outflow sculpts the nebula and interacts with the material hurled out by the primary in past eruptions. Without the companion's influence, the Homunculus Nebula and surrounding environment might look very different. The companion star also provides astronomers with crucial clues about the system's dynamics. Because the two stars orbit each other in such an eccentric path, their interactions allow scientists to measure aspects of their masses, wind speeds, and radiation outputs that would otherwise remain hidden. For instance, periodic dips in X-ray brightness occur when the companion plunges behind the dense winds of the primary, effectively giving scientists a probe into the primary's outer layers. By studying these cycles, astronomers can infer details about both stars' structures and behaviors, something rarely possible in other massive star systems. And while the companion is smaller than the primary, it is not any less doomed. A star with even 30 solar masses will burn through its life in just a few million years, ending in its own supernova explosion. If Eta Carinae's primary somehow managed to delay its death, the companion could, in theory, go supernova first. But more likely, both stars will reach their catastrophic ends relatively close together in cosmic time, perhaps even influencing one another's explosions in ways we have never witnessed. Imagine, for instance, the possibility of a double supernova event in one system, a fireworks display on a galactic scale. The relationship between these two giants is a study in extremes, one bloated, unstable, and shining at the Eddington limit, the other leaner, hotter, and more aggressive with its winds. Together, they create a storm of interactions that make Eta Carinae one of the most fascinating systems in the universe. The companion star is not overshadowed so much as it is interwoven into the very identity of Eta Carinae. Without it, the system would not behave as it does, nor would it have the same violent and unpredictable character. In the end, the companion reminds us of an important truth. In astronomy, smaller is relative. A star tens of times the mass of the Sun is still a titan, capable of ending its life in a cataclysm that would outshine galaxies. In Eta Carinae's case, the so-called secondary star is not a side character but a co-star, one whose presence ensures that the system remains unstable, explosive, and endlessly captivating to astronomers. One of the most violent and defining features of Eta Carinae is the ferocity of its stellar winds. Both the primary and companion stars are not simply shining, they are bleeding material into space at catastrophic rates, driving off vast quantities of gas at speeds so great that they would make a speeding bullet look motionless. These winds are not gentle breezes, they are hurricanes of plasma, moving at thousands of kilometers per second, reshaping the surrounding nebula and creating some of the most extreme environments in the galaxy. The primary star, bloated and unstable, loses mass through winds that are dense and heavy, but slower compared to its companion. Estimates suggest it sheds the equivalent of our Sun's mass every 10,000 years. An astounding figure, given that the Sun itself will only lose a fraction of its mass over its entire 10 billion-year lifetime. These winds blast out into space at speeds of around 500 to 600 kilometers per second. To put that in perspective, A spacecraft launched from Earth takes months to reach Mars. Eta Carinae's winds could cover that same distance in just a few hours. The companion star, on the other hand, while smaller, is more compact and hotter, producing much faster but less dense winds. Its stellar outflows roar outward at 3,000 kilometers per second, nearly 1% of the speed of light. These winds may not carry as much mass as those of the primary, but their speed makes them incredibly energetic, capable of slamming into the surrounding environment with devastating force. Where these two winds meet, they create a collision zone of unimaginable violence. The slower, denser winds of the primary are struck head-on by the faster, sharper winds of the companion, creating a shock front where gas is compressed, heated, and accelerated to extreme energies. Temperatures in this zone can rise into the tens of millions of degrees, hot enough to generate powerful X-ray radiation detectable even from Earth. This violent interaction is not static, it shifts and pulses as the two stars orbit each other every 5.5 years, creating cycles of increasing and decreasing intensity in the X-rays astronomers observe. The sheer scale of mass loss from these winds is mind-boggling. The primary star alone is thought to be shedding material at a rate of about 1/10,000 of a solar mass per year. That sounds small, but it's enormous when you remember the Sun would need billions of years to lose even a single % of its mass. Over thousands of years, Eta Carinae's winds have carved away enough of the star that it is steadily peeling itself apart, layer by layer. This relentless process is partly why astronomers believe the star's end is near. It is hemorrhaging material too quickly to survive for long. The winds also play a starring role in shaping the Homunculus Nebula, the twin-lobed cloud of gas and dust surrounding Eta Carinae. The Great Eruption in the 1840s expelled tens of solar masses of material into space, but the winds since then have continued to sculpt and mold that ejected matter. They push against it, accelerate it, and interact with it, creating shockwaves and arcs of glowing gas visible in incredible detail through telescopes like Hubble. In this way, Eta Carinae is constantly rewriting its own environment, a star system painting a canvas of destruction and beauty with its own expelled matter. Another fascinating aspect of these winds is how they create instability within the system itself. The interaction between the winds causes turbulence, instigating chaotic variations in brightness and radiation output. Sometimes, these changes are periodic, tied to the orbital cycle of the stars. Other times, they are unpredictable, sudden outbursts that hint at deeper instabilities within the primary. For astronomers, this makes Eta Carinae both frustrating and thrilling to study. It never behaves the same way twice, and its winds ensure it is always in flux. The winds also remind us of just how inefficient massive stars are at holding onto their mass. Unlike our Sun, which quietly sips its fuel and retains most of its structure, Eta Carinae is constantly shedding itself into space. Every gust of stellar wind carries away not just mass, but the raw material for future stars and planets. In this way, Eta Carinae is already seeding the interstellar medium with heavy elements forged in its core, enriching the galaxy long before its final explosion. If one were somehow able to stand near Eta Carinae, a thought experiment only, because no spacecraft or human could survive the radiation, one would encounter a storm beyond comprehension. The winds would not be air but searing plasma, rushing outward faster than anything on Earth could withstand, accompanied by torrents of radiation that would strip molecules apart. It is a place of such violence that the very fabric of matter is constantly ripped, reformed, and hurled outward into the void. For astronomers, these stellar winds are not just destructive, they are a gift. The X-rays generated by the colliding winds provide critical insights into the structure, temperature, and dynamics of the system. By studying them, scientists can piece together details about the mass of the stars, the speed of their outflows, and even the orientation of their orbit. In a sense, the winds serve as the diagnostic signals of Eta Carinae's instability, offering a rare opportunity to study stellar physics under the most extreme conditions nature allows. At the heart of Eta Carinae's chaos lies one of the most extraordinary phenomena in astrophysics, the wind collision zone. This is where the dense, slower winds of the swollen primary star crash headlong into the faster, thinner winds of the smaller but hotter companion. The result is a violent, turbulent boundary where forces on an unimaginable scale collide, literally creating a cosmic battlefield of shockwaves, radiation, and searing plasma. To understand just how extreme this zone is, imagine two fire hoses blasting directly into each other, but instead of water, they're ejecting superheated plasma moving at hundreds to thousands of kilometers per second. One hose, the primary star, pours out a thick, heavy torrent, while the other, the companion, blasts a faster but lighter stream. When the two flows meet, they don't cancel each other out. Instead, they create a compressed interface where material is squeezed, heated, and hurled outward at astonishing velocities. This zone is not a static wall but a writhing, curved shock front that bends under the competing pressures of the two winds. Because the companion star's winds are much faster, up to 3,000 km per second, compared to the primary's slower 500 to 600 km per second, the shock structure is pushed closer to the primary star, wrapping around it like a bow wave around a ship. The companion effectively carves out a cavity in the dense wind of the primary, creating a space where matter is constantly colliding, compressing, and radiating energy. The most dramatic outcome of these collisions is the generation of X-ray radiation. When the stellar winds slam into each other, the shockwaves heat the gas to tens of millions of degrees, hotter than the core of most stars. At such temperatures, the gas emits high-energy photons in the X-ray part of the spectrum. From Earth, telescopes like NASA's Chandra X-ray Observatory and ESA's XMM Newton can detect these emissions, allowing scientists to see the violence of Eta Carinae's wind collisions directly. In fact, Eta Carinae is one of the brightest sources of variable X-rays in the sky, a beacon of energy that reveals the ferocity of its internal struggle. These X-rays don't remain constant. They fluctuate dramatically over the course of the system's 5.5-year orbital cycle. When the two stars move closer together in their highly elliptical orbit, the collision zone becomes more intense, with higher temperatures and brighter X-ray output. But during the brief period when the companion passes behind the dense wind of the primary, the X-ray emission plunges. It's as though the system takes a deep breath, hiding its fury, only to unleash it again when the stars move apart. This cyclical variability is one of the reasons astronomers are able to study Eta Carinae's inner workings in such detail. The system provides a natural laboratory for observing how colliding winds evolve over time. Beyond the radiation, the wind collision zone also produces shockwaves that ripple outward, sculpting the surrounding environment. The gas compressed in the shock front doesn't simply vanish, it is redirected, flung into arcs and spirals that can extend light-years into space. These structures are partly responsible for the chaotic appearance of the material surrounding Eta Carinae, contributing to the complex knots and filaments seen in images of the Homunculus Nebula and its halo. But the collision zone isn't only about destruction, it also holds scientific treasure. By analyzing the X-rays and the timing of their variations, astronomers can infer critical information about both stars. For example, the strength and speed of the companion's wind can be deduced from how deeply it carves into the primary's outflow. Similarly, the density and extent of the primary's wind can be measured by studying how much it absorbs or blocks the X-rays during eclipses. In a way, the wind collision zone is like an X-ray CT scan of the system, revealing details that would otherwise remain hidden beneath the star's blinding glare. Interestingly, this violent region may also play a role in triggering larger events, such as eruptions. Some theories suggest that during periastron, when the companion star plunges deep into the primary's wind, the gravitational and wind-driven disturbances can destabilize the primary's outer layers, possibly setting off massive outbursts like the one seen in the 1840s. If true, it means the wind collision zone is not just a byproduct of the system but a driver of its long-term instability. There's also a tantalizing possibility that the colliding winds could accelerate particles to nearly the speed of light, creating cosmic rays. If this is the case, Eta Carinae would not only be a luminous beacon of X-rays but also a factory of high-energy particles that could travel across the galaxy. While Earth is too far away to feel their direct effects, these cosmic rays would contribute to the energetic environment of the Milky Way, another way Eta Carinae impacts more than just its immediate neighborhood. Ultimately, the wind collision zone is a perfect symbol of Eta Carinae's duality: beauty intertwined with violence, chaos harnessed into scientific revelation. It is a place where two giants meet not in harmony but in eternal struggle, their clash lighting up the cosmos with radiation powerful enough to pierce 7,500 light-years of space and still reach our telescopes. Without it, Eta Carinae would be less dangerous, less fascinating, and far less understood. With it, the system becomes one of the most spectacular laboratories for extreme astrophysics that humanity has ever encountered. When we think of stars that have left a mark on human history, we often picture supernovae, sudden stellar deaths that light up the heavens and astonish observers on Earth. Yet Eta Carinae stands apart, for in the 1840s, it gave the world a spectacle so brilliant, so overwhelming, that it rivaled even the most powerful stellar explosions, but without actually dying. This was the Great Eruption, one of the most mysterious and extraordinary outbursts ever recorded in astronomy. In the early 19th century, Eta Carinae was known to astronomers, but it was not regarded as particularly unusual. It was bright, certainly, but there were many stars visible in the southern skies that drew attention. Then, beginning around 1837, something began to change. The star suddenly grew brighter, not by a little, but by orders of magnitude. For the next decade, its light surged and flickered, as though the star itself were gasping for survival. By 1843, it had become the second brightest star in the entire night sky, outshone only by Sirius, which is much closer to us. To give a sense of scale, Eta Carinae, located 7,500 light-years away, was shining with such ferocity that it eclipsed nearly every other star in brightness. Imagine a lighthouse so powerful that it could be seen not just across oceans, but across continents. That is what Eta Carinae did. It turned itself into a beacon of cosmic light, one that startled stargazers across the globe. The eruption was not just a matter of increased brightness. Historical accounts suggest Eta Carinae's behavior was dramatic and unpredictable. Some nights it would blaze, nearly rivaling Sirius. Other times, it would dim slightly, only to surge again. For observers who tracked the skies meticulously, this was both a wonder and a puzzle. Remember, this was decades before the physics of nuclear fusion or the structure of massive stars was understood. For many astronomers of the 19th century, Eta Carinae's outburst seemed almost supernatural. What was actually happening? Today, scientists believe the Great Eruption was caused by the instability of the primary star, likely exacerbated by the gravitational and wind-driven influence of its companion. The star expelled a staggering 10 to 20 times the mass of our Sun in just a few short decades. That is more mass than most stars will ever lose across their entire lifetimes, thrown off in a convulsion so violent it created a nebula, the Homunculus Nebula, that still surrounds Eta Carinae to this day. The energy released during the Great Eruption was comparable to a small supernova, though not quite enough to destroy the star. Astronomers call this kind of event a supernova imposter, a stellar tantrum that mimics the brilliance of a true supernova, but leaves the star alive, though wounded and unstable. Eta Carinae's outburst is one of the most dramatic examples of such imposters ever witnessed. For over a decade, the sky show continued. From 1837 to the mid-1850s, Eta Carinae remained astonishingly bright, and even after it faded, it did not return to its former state. Instead, it slipped into obscurity, dimming until it became invisible to the naked eye by the late 19th century. For a while, astronomers thought the star might have finally burned out. But then, in the 20th century, it began to brighten again, and continues to do so even today, reminding us that its story is far from over. The Great Eruption was not only a spectacular display but also a defining event in the study of massive stars. It showed astronomers that stars could have catastrophic outbursts without actually dying, challenging the neat categories of stellar evolution that had been imagined at the time. Even now, nearly 2 centuries later, the event is still puzzling. What exactly triggered it? Was it internal instability in the primary star? Was it a near collision with the companion during periastron? Or was it some combination of factors we still don't fully understand? For modern astrophysics, the Great Eruption serves as a reminder of the unpredictability of giant stars. It was, in a sense, a warning shot, Eta Carinae demonstrating what it is capable of, hinting at the far more destructive finale that awaits it in the form of a supernova or hypernova. The outburst also seeded the space around the system with the building blocks of the Homunculus Nebula, which now acts as both a monument to the eruption and a laboratory for scientists trying to decode its secrets. Imagine being a skywatcher in the 1840s, with no telescopes like Hubble or Chandra, no understanding of nuclear fusion, no knowledge of stellar winds. You look up at the southern sky, and suddenly, a familiar constellation is dominated by a new light, dazzling and unexplainable. It must have been both awe-inspiring and unsettling, a reminder that the heavens above are not static, but alive and capable of sudden fury. Today, we recognize the Great Eruption as one of the most extraordinary astronomical events ever witnessed by humans. It didn't just change Eta Carinae, it changed astronomy. It opened questions about how stars lose mass, how binary systems interact, and how instability shapes the lives of the most massive stars in the universe. And it ensured Eta Carinae's place in history, not just as a dangerous star, but as a living mystery, a cosmic drama still unfolding before our eyes. If Eta Carinae's Great Eruption was the performance, then the Homunculus Nebula is the stage it left behind, a haunting and beautiful monument to one of the most violent stellar tantrums in recorded history. This gigantic cloud of gas and dust, ejected during the mid-19th century, now surrounds Eta Carinae like a shroud, glowing with the scattered light of the unstable stars hidden inside. It is both a scar of violence and a work of cosmic art, telling us more about the eruption than words alone ever could. The homunculus, whose name comes from the Latin word for little man, does not look little at all. It is vast on human scales, stretching nearly a light year from end to end. To put that in perspective, a single lobe of the nebula is larger than the entire solar system, many thousands of times over. When astronomers look at it through powerful telescopes such as the Hubble Space Telescope, they see a spectacular twin-lobed structure, like two giant balloons pressed together at their bases. This bipolar shape is the direct result of the eruption. Instead of material flying outward evenly in all directions, it was funneled into two massive lobes, perhaps due to the influence of the binary companion or the star's own rotation. The gas and dust making up the homunculus is enormous in both volume and mass. Astronomers estimate that the eruption ejected about 10 to 20 solar masses worth of material. Imagine the sun itself being torn apart and flung into space 10 times over. All of that mass is now floating in the nebula, forming thick clouds that scatter light and glow under the intense radiation of Eta Carinae's central stars. In fact, the nebula is so dense in some regions that it completely blocks visible light from the stars, making direct observation of the primary and companion nearly impossible. Instead, astronomers must rely on infrared and X-ray telescopes to peer through the dusty veil. The homunculus isn't just a pretty shape, it is a living laboratory of astrophysics. Inside those lobes are shock fronts, arcs, filaments, and knots of gas, each carrying the fingerprints of the violent forces that created them. Some regions glow brightly in infrared, where dust warmed by the central stars radiates its heat. Others shine in visible light, lit up by ultraviolet radiation escaping from Eta Carinae. The nebula as a whole acts like a fossilized record of the eruption, preserving not just the mass ejected, but the directions, speeds, and energies involved. By studying it, astronomers can essentially reconstruct the Great Eruption like forensic scientists piecing together a crime scene. One of the most fascinating aspects of the homunculus is its bipolar symmetry. Both lobes are remarkably similar in size and shape, as though the eruption blasted material outward in two opposite directions simultaneously. This symmetry suggests the outburst wasn't just a chaotic explosion, but something shaped by deeper forces. Some theories point to the binary companion. As the two stars interacted, gravitational and wind-driven dynamics may have funneled the eruption into poles rather than allowing it to expand equally in all directions. Others suggest rapid rotation in the primary star may have directed the outflow. Whatever the cause, the result is one of the most iconic structures in astronomy, instantly recognizable in images as the double bubble of Eta Carinae. The nebula is not static. Over the nearly 2 centuries since it formed, it has been expanding outward at speeds of hundreds of kilometers per second. By measuring this expansion, astronomers have been able to date the eruption with remarkable precision, confirming that the bulk of the ejected material corresponds to the outburst of the 1840s. Like a time capsule, the homunculus continues to drift away, carrying with it the story of that catastrophic decade. And yet, the homunculus is not just an artifact of the past, it is also an ongoing participant in Eta Carinae's drama. The dense dust and gas interact with the fierce stellar winds pouring out of the central stars, creating new shocks and sculpting intricate patterns across its surface. The radiation from Eta Carinae ionizes portions of the nebula, making them glow, while other regions remain dark and opaque, concealing mysteries we still struggle to uncover. In some places, the nebula acts like a mirror, reflecting the light of the hidden stars inside and allowing astronomers to study their spectral fingerprints indirectly. For observers on Earth, the homunculus is both a shield and a gift. It conceals Eta Carinae's core, preventing us from seeing the most intimate details of the binary directly. But it also amplifies the star's grandeur, giving us a structure we can image, map, and study with incredible precision. Without the homunculus, the Great Eruption might have left behind nothing more than vague historical accounts. Instead, we have a glowing relic that continues to tell its story across the centuries. In many ways, the Homunculus Nebula is as famous as Eta Carinae itself. Its stunning bipolar shape, captured in breathtaking Hubble images, has become a symbol of stellar extremes, often appearing in textbooks, documentaries, and research papers. For scientists, it serves as a rare chance to study the immediate aftermath of a massive eruption, something almost never observed in real time. For the public, it is a reminder that the universe is capable of sculpting beauty out of violence, leaving behind monuments that are as mesmerizing as they are destructive. When Eta Carinae unleashed the Great Eruption in the 1840s, the scale of energy released was nothing short of staggering. For decades, astronomers struggled to comprehend how a star could erupt with such ferocity, rivaling the brilliance of a supernova, and yet survive. Today, we classify events like this as supernova imposters, because they mimic many of the outward signs of a stellar death without reaching the final destructive threshold. To understand just how extraordinary Eta Carinae's eruption was, we need to compare its energy to that of a true supernova. A typical supernova represents the death of a massive star, releasing around 10 to the power of 44 joules of energy, an amount so immense that it briefly outshines entire galaxies. During the event, much of the star's outer material is blown into space at thousands of kilometers per second, while the core collapses into either a neutron star or a black hole. That finality is what separates a supernova from any other stellar outburst. Eta Carinae's eruption didn't quite reach those levels, but it came shockingly close. Astronomers estimate that during the 1840s, the star released 10 to the power of 49 ergs of energy, that's about 10 to the power of 42 joules. This means the eruption was only about 1% of the total energy output of a supernova, but even that fraction is almost inconceivable on human scales. To put it differently, Eta Carinae's Great Eruption released more energy in a few decades than our Sun will radiate in its entire 10 billion-year lifetime. The mass ejected during the event also reflects this immense energy. Between 10 and 20 solar masses of material were blasted into space, forming the Homunculus Nebula that now surrounds the star. For comparison, our Sun has been shedding solar wind material for billions of years, and in that time, it has lost less than 0.1% of its total mass. Eta Carinae managed to throw away the equivalent of several suns in just a human lifetime. That feat alone speaks to the eruption's near-supernova scale. Yet what's even more remarkable is that the eruption did not destroy the star. Unlike a supernova, where the core collapses and the star's life ends, Eta Carinae's outburst was more like a catastrophic release valve. The primary star vented a colossal fraction of its mass but managed to cling to survival. This is one reason the event is often labeled a failed supernova, a detonation that had all the fury of a stellar death but lacked the final collapse. Comparing the two further highlights Eta Carinae's uniqueness. A true supernova is over in weeks or months, its light curve rising sharply and then fading. The Great Eruption, however, lasted for more than a decade. Instead of a single explosive flash, it was a drawn-out convulsion, as though the star were thrashing violently against its own instability, expelling energy and mass in fits and bursts. This prolonged nature sets it apart from almost every other type of stellar outburst we know. Another astonishing detail is how visible the eruption was from Earth. For Eta Carinae to shine as the second brightest star in the night sky, despite being 7,500 light-years away, its energy output had to be phenomenal. Had it been located just a few hundred light-years away, it might have been so bright that it could cast shadows at night, or even be visible in broad daylight, much like a true supernova. The eruption also released energy in different forms. Much of it went into light and radiation, which reached Earth and dazzled observers. Another large portion was carried away in the kinetic energy of the ejected gas, the material we now see in the Homunculus Nebula. Still more was likely carried by intense winds and shockwaves that heated and disturbed the surrounding interstellar medium. In total, the event demonstrated just how many ways a massive star can release energy short of total collapse. For astronomers, this makes Eta Carinae's Great Eruption not just an oddity, but a benchmark for extreme stellar behavior. By comparing it with true supernovae, we learn that stars can release near-apocalyptic levels of energy without dying outright, a process that may occur more often in the universe than we once thought. Other supernova imposters have since been observed in distant galaxies, but none match the grandeur of Eta Carinae's 19th-century convulsion, partly because we have the benefit of both historical records and modern telescopes to study its aftermath. In summary, the energy of the Great Eruption was a paradox, far too large to be explained by ordinary stellar winds or minor instability, yet not large enough to end in death. It was as if Eta Carinae tore itself apart and somehow stitched itself back together again, wounded but alive. That razor's edge, between survival and destruction, is what makes this event so endlessly fascinating and so haunting. Eta Carinae didn't just show us the scale of stellar violence, it showed us how close a star can come to dying without actually crossing the threshold. The survival of Eta Carinae after the Great Eruption is one of the most baffling and fascinating puzzles in modern astrophysics. By all appearances, the eruption had every hallmark of a stellar death. It shone brighter than almost any other star in the sky, it expelled 10 to 20 times the mass of our Sun in a violent outflow, and it released energy on a scale only rivaled by supernovae. And yet, when the dust settled, the star was still there. Not only alive, but continuing its turbulent journey toward an eventual end. Why did Eta Carinae survive when so many other stars in similar situations would have perished? The answer lies in the difference between an eruption and a true supernova. In a core collapse supernova, the heart of the star, the nuclear fusion engine, runs out of fuel, gravity takes over, and the core collapses inward in milliseconds. This collapse rebounds outward in a shockwave, ripping the star apart and leaving behind either a neutron star or a black hole. Nothing of the outer star survives intact. The Great Eruption, however, never reached that stage. Eta Carinae's eruption was instead a surface-level catastrophe, driven by instability in its outer layers rather than the collapse of its core. The primary star is so massive, estimated between 100 and 150 suns, that its radiation pressure is nearly at the Eddington limit, the point at which the outward push of light equals the inward pull of gravity. Living so close to this edge means even slight instabilities can cause the star's outer layers to break loose, like steam blowing the lid off a pressure cooker. The Great Eruption was one such failure, a runaway release of radiation and gas that blew off huge chunks of the star's outer envelope without destabilizing the nuclear burning core. In a sense, Eta Carinae survived because it was too massive to die in that moment. Its gravity was so overwhelming that even after ejecting tens of solar masses of material, enough of the star's bulk remained to hold itself together. Where a smaller star might have lost enough mass to completely unravel, Eta Carinae's vast reserves of matter allowed it to keep burning, albeit in a scarred and weakened state. The presence of its companion star may also have played a role in the survival. The secondary star's fierce winds and gravitational pull likely contributed to funneling material away from the primary, shaping the Homunculus Nebula into its now iconic bipolar form. While this interaction triggered or intensified the eruption, it may also have prevented a full-scale collapse by redirecting the instability outward, allowing the core to remain intact. In this way, the companion acted both as an instigator and an unlikely savior, helping the primary release its fury without total destruction. There's another factor, the timescale of the eruption. A supernova is over in weeks to months, but Eta Carinae's outburst lasted more than a decade, from the late 1830s to the early 1850s. Instead of a single catastrophic event, the star went through a series of convulsions, each one blowing off more material but giving the star time to stabilize in between. This staggered release of energy may have spared it the fate of immediate death. It was, in effect, a controlled burn rather than a total collapse. From today's perspective, Eta Carinae's survival is both a blessing and a curse. A blessing because it allows astronomers to study the system in detail, using modern telescopes to analyze its winds, eruptions, and X-ray emissions. A curse because its continued instability means it remains one of the most dangerous ticking time bombs in our galaxy, destined sooner or later to erupt again, this time as a true supernova or even a hypernova. The Great Eruption also highlights an important truth about massive stars. Their deaths are rarely clean or simple. Instead of quietly fusing hydrogen until they collapse, these giants often go through violent fits and starts, shedding layer after layer in colossal outbursts long before the final explosion. Eta Carinae is a prime example of this messy path to death, one of the very few we've been fortunate enough to witness up close. Ultimately, Eta Carinae survived because the eruption, for all its violence, was not enough to reach the core. It blew off the skin but left the heart beating. The nuclear engine at the star's center continues to fuse elements, powering its blinding light and ferocious winds, even as its outer layers remain unstable and unpredictable. It was not spared because it is stable, it was spared because its immense mass and gravity bought it more time. Time, however, that will one day run out. In many ways, this survival makes Eta Carinae even more awe-inspiring. It is not just a star that erupted, it is a star that endured, limping away from an event that would have ended nearly any other star's life. Its survival ensures that humanity has front-row seats to one of the universe's greatest ongoing dramas, the long, chaotic prelude to one of the most spectacular deaths the galaxy will ever see. One of the most captivating and frustrating aspects of Eta Carinae is its unpredictable brightness. Unlike most stars, whose light output is fairly stable and follows well-understood cycles, Eta Carinae behaves like a cosmic mood swing, brightening and dimming in ways that challenge astronomers to decode its underlying causes. This erratic behavior has turned it into both a laboratory of extremes and a riddle that modern science is still trying to solve. The story begins with the Great Eruption of the 19th century. During that decade-long convulsion, Eta Carinae surged in brilliance until it became the second brightest star in Earth's night sky, rivaling Sirius despite being nearly 7,500 light-years farther away. Then, as abruptly as it had brightened, it faded. By the 1870s, just a few decades after its spectacular outburst, the star had grown so faint that it nearly vanished from naked-eye visibility. This dramatic fall puzzled astronomers of the time. How could a star flare to near supernova luminosity only to fade almost completely within a human lifetime? Since then, Eta Carinae has never stopped changing. Its brightness has wavered over the years, sometimes brightening significantly, sometimes dimming, always keeping observers guessing. For example, in the mid-20th century, the star was faint and obscure, barely detectable without telescopes. But by the late 1990s and early 2000s, it began to brighten again, once more becoming a prominent object in southern skies. Today, it shines more brightly than it did for most of the 20th century, though still not as dazzling as during its 19th century outburst. What drives these fluctuations? The answer is complex, because Eta Carinae is a binary system, and the interaction of its two massive stars plays a key role. Every 5.5 years, when the two stars reach their closest approach in their elongated orbit, astronomers observe a dip in brightness and X-ray emissions. This is tied to the wind collision zone, where the powerful stellar winds of the two giants crash into each other. As the stars swing together, the collision becomes more chaotic, the shockwaves grow stronger, and dense material clouds the region. This turbulence can block light, absorb X-rays, and alter the brightness we see from Earth. Once the stars separate again, conditions stabilize, and the system's brightness shifts. But this orbital cycle alone doesn't explain everything. The larger star, with its unstable outer layers, undergoes irregular eruptive outflows that can suddenly obscure or enhance its light. Imagine the star coughing up massive clouds of gas and dust. Sometimes these clouds dim the system as they drift in front of our line of sight, while other times they reflect or scatter light, making the star appear brighter. Combined with the dynamic sculpting of the Homunculus Nebula, this creates a constantly shifting visual profile. What makes Eta Carinae especially intriguing is that these fluctuations don't follow a neat, predictable pattern. Astronomers can anticipate the 5.5-year orbital changes, but the irregular long-term brightening and dimming are harder to pin down. Some researchers propose that these fluctuations represent the star's slow recovery from the Great Eruption, as it continues to expel unstable outer material. Others suggest they are precursors of even greater instability, potential warning signs that the star is creeping toward another massive outburst, or even its final collapse. From a practical standpoint, Eta Carinae's unpredictable brightness makes it one of the most closely monitored stars in the galaxy. Observatories around the world keep watch on it, both in visible light and across the electromagnetic spectrum, from radio waves to X-rays. Even small changes in brightness are treated as clues, pieces of a larger puzzle that may eventually reveal when and how this star will meet its end. To the naked eye, these changes can feel almost supernatural. Imagine a star that fades nearly into invisibility, then reawakens decades later with renewed vigor, glowing brighter than it has in generations. For 19th-century astronomers who documented its behavior, this must have seemed like watching a celestial phoenix, dying, being reborn, and changing form before their very eyes. Even today, with all our modern science, Eta Carinae's erratic light feels like a reminder of how fragile our predictions are when dealing with such extreme cosmic phenomena. In the grand scheme, the star's fluctuations are signals of instability, a system living on the edge, always threatening to tip into chaos. Its unpredictable brightness serves as a warning light on the dashboard of the universe. Eta Carinae is not stable, not safe, and certainly not finished. Whether its next major brightening will herald another eruption or mark the prelude to a true supernova is something astronomers can only speculate about. And that uncertainty is part of what makes it so mesmerizing. Eta Carinae's story inevitably leads to one chilling and awe-inspiring question: when will it die? Astronomers are almost certain that this unstable giant is nearing the end of its stellar life. Its size, instability, and violent history leave little doubt that it will one day erupt as a supernova, or perhaps something even more catastrophic. The real uncertainty is when. Will it happen within our lifetimes? Or will the star cling to survival for thousands of years more before collapsing under its own weight? Massive stars like Eta Carinae burn through their nuclear fuel at breakneck speeds. Where a star like our Sun leisurely fuses hydrogen for about 10 billion years, a star with 100 to 150 solar masses has only a few million years before it exhausts. Its core, Eta Carinae, is already well along this accelerated timeline. Based on models of stellar evolution, it is living in its final stages, with only a thin margin of time left before its nuclear processes can no longer support its massive bulk. Astronomers estimate that the explosion could occur anytime within the next several thousand years. In cosmic terms, that's the blink of an eye. To put it in perspective, if the history of Earth were compressed into a single year, Eta Carinae's final explosion might occur sometime within the last second before midnight on New Year's Eve. That's how close it is in astronomical terms. The evidence for this impending doom lies in the star's current condition. Its instability, manifested through violent winds, unpredictable brightness, and historical outbursts, shows that the star is already struggling to maintain balance. The Great Eruption was a clear sign of a star in distress, shedding mass in a desperate attempt to relieve internal pressures. Stars don't typically undergo such catastrophic events unless they're approaching the limits of their endurance. In many ways, Eta Carinae's behavior is like the rattle of a failing engine, ominous symptoms that warn of inevitable breakdown. When Eta Carinae finally does collapse, the resulting supernova will be one of the most spectacular events in galactic history. Astronomers predict it will shine so brightly that it could be visible even in broad daylight, outshining the moon for weeks or even months. It would briefly rival the brilliance of the full moon, turning night into something almost alien. People across Earth would be able to look up and see, with their naked eyes, the death of a giant star from thousands of light years away. But while the spectacle will be breathtaking, the physics behind it will be violent beyond imagination. In its death throes, Eta Carinae's core will collapse in a fraction of a second, triggering shockwaves that rip through its layers and hurl its outer material into space at thousands of kilometers per second. This explosion will release more energy in a few moments than the Sun will radiate across its entire lifespan. The material blasted into the galaxy will enrich the surrounding space with heavy elements like iron, gold, and uranium, ingredients essential for the formation of new planets and life. It is not an exaggeration to say that Eta Carinae's future death will reshape its corner of the galaxy. The expanding shockwave will plow into the Homunculus Nebula, shredding and dispersing the material from its earlier eruption. Over thousands of years, the explosion's debris will spread outward, mixing with interstellar gas and seeding the cosmos with new matter that may one day form new star systems. Despite the magnitude of this impending event, astronomers caution against thinking of it as imminent in human terms. Any time in the next few thousand years is both soon and impossibly far. There's no way to predict whether Eta Carinae will explode tomorrow, in our grandchildren's lifetime, or long after human civilization has changed beyond recognition. From the star's perspective, the final collapse is inevitable. From ours, it's a waiting game. Yet this waiting is part of what makes Eta Carinae so captivating. Humanity rarely gets to watch a massive star in its final countdown, knowing that the end is close but not knowing when the curtain will fall. Every fluctuation in brightness, every burst of X-rays, every ripple of instability could be a prelude to the final act, or just another convulsion in a long series of death throes. Eta Carinae is, quite literally, a ticking time bomb in the sky. Astronomers around the globe keep constant watch on it, not only to anticipate its demise but also to study the warning signs. By learning how Eta Carinae behaves in its final stages, we gain a blueprint for understanding other massive stars nearing their end. If it explodes in our lifetimes, it will be one of the greatest opportunities for scientific discovery in history, offering an unprecedented window into the physics of stellar death. But whether it happens tomorrow or 10,000 years from now, the certainty remains. Eta Carinae's end will come, and when it does, the universe will witness one of the brightest and most violent events since humans first looked to the stars. When astronomers contemplate Eta Carinae's ultimate fate, they often speak of a supernova. But there's another, even more extreme possibility: a hypernova. While a supernova already represents one of the most violent events in the universe, a hypernova is in a league of its own, a cosmic detonation so powerful that it can shake entire galaxies and create conditions for the most energetic phenomena we know of, such as gamma-ray bursts. And Eta Carinae, with its sheer size and instability, is a prime candidate for such an extraordinary finale. So what exactly is a hypernova, and how does it differ from a supernova? A hypernova is a term used to describe the collapse of an exceptionally massive star, generally one with a core far larger than that of the stars that produce normal supernovae. When these stars reach the end of their nuclear fuel, their cores collapse into black holes rather than neutron stars. The collapsing core pulls in surrounding stellar material at astonishing speeds, creating a swirling accretion disk that powers relativistic jets, narrow beams of energy moving near the speed of light. These jets punch their way out of the star and release 10 times or more the energy of a typical supernova. For Eta Carinae, the possibility of a hypernova is tied to its enormous mass. The primary star alone may still have over 100 solar masses even after shedding much of itself during the Great Eruption. If its core collapses, the sheer scale of its mass could be enough to trigger the conditions necessary for a hypernova. Not just the collapse of the core, but the creation of those powerful jets that make hypernovae so fearsome. The energy output of a hypernova is staggering. Where a standard supernova radiates the equivalent of 10 billion suns for a short time, a hypernova can release 100 billion suns worth of energy, making it among the brightest and most destructive explosions in the universe. Such an event in Eta Carinae would dwarf nearly everything else visible in the night sky. From Earth, 7,500 light-years away, it could appear so bright that it might cast shadows at night, rival the full moon in intensity, and remain visible for months or even years. Another consequence of a hypernova is the potential for a gamma-ray burst, GRB, one of the most lethal cosmic phenomena known. These bursts are thought to originate from the jets launched during a hypernova, focused into narrow beams that can travel across galaxies. If Earth were unlucky enough to be aligned with one of those beams, the consequences could be devastating, as I'll explain in the next section. Fortunately, most studies suggest the axis of Eta Carinae's rotation, and therefore the likely direction of any jets, is not pointed directly at us, making such a direct hit unlikely. Still, the mere possibility underscores just how dangerous this star is. There is also the matter of what comes after a hypernova. If Eta Carinae ends this way, its collapse will likely leave behind not a neutron star but a black hole of considerable mass. That black hole would remain as a permanent scar of the event, a compact remnant of a once mighty giant. It would also mark the transformation of one of the most luminous and unstable stars in the Milky Way into one of the most mysterious and invisible objects, a well of gravity from which not even light can escape. For astronomers, the chance to observe a hypernova up close, relatively speaking, would be unprecedented. Most hypernovae we've detected are in distant galaxies, often millions or even billions of light-years away. Eta Carinae is in our galactic backyard by comparison. If it were to go hypernova in our lifetime, the data we could collect would revolutionize our understanding of how the most massive stars die, how black holes are born, and how heavy elements are scattered into the galaxy. The tantalizing question remains: will Eta Carinae end as a supernova or a hypernova? Current models cannot say with certainty. Some argue its instability and mass loss may reduce it enough that a standard supernova is more likely. Others counter that even after its violent eruptions, it remains massive enough to cross the threshold into hypernova territory. What all agree on is that either outcome will be monumental. In the end, Eta Carinae is the embodiment of cosmic suspense. It could explode with the familiar brilliance of a supernova, or it could unleash the unimaginable violence of a hypernova, rewriting everything we know about stellar death in the process. The truth is, We won't know until it happens. And when it does, the spectacle will remind humanity of just how small we are compared to the forces that shape the universe. One of the most chilling possibilities tied to Eta Carinae's eventual death is the chance that it could unleash a gamma-ray burst, GRB. These bursts are among the most destructive forces in the cosmos, capable of sterilizing entire planets if they happen to be in the wrong place at the wrong time. If Eta Carinae were to end its life as a hypernova, it could send out twin beams of high-energy gamma rays, each one focused like a cosmic laser, carrying more destructive power in a matter of seconds than the Sun will emit in its entire lifetime. So what exactly is a gamma-ray burst? A GRB is an extremely intense flash of gamma radiation, the most energetic form of light in the electromagnetic spectrum. They are thought to be produced when a massive star collapses into a black hole and generates powerful relativistic jets. These jets slice through the collapsing star, breaking free into space and releasing energy equivalent to all the stars in the observable universe shining at once, compressed into a few seconds or minutes. If Eta Carinae were to create such jets, and if one of them were directed toward Earth, the consequences could be catastrophic. Gamma rays are ionizing radiation, meaning they can strip electrons from atoms and break apart molecules. A GRB hitting Earth's atmosphere would destroy the ozone layer, leaving the surface exposed to lethal doses of ultraviolet radiation from the Sun. Within days to weeks, ecosystems could collapse. DNA damage in living organisms would spike, food chains would unravel, and mass extinctions could occur. Scientists even suspect that past gamma-ray bursts may have caused some of Earth's ancient extinction events. Fortunately, the danger is not as apocalyptic for us as it might sound at first. For a GRB to be lethal to Earth, two conditions must be met. First, Eta Carinae must collapse as a hypernova, not just a supernova. And second, one of the narrow gamma-ray beams, only a few degrees wide, must be aimed almost perfectly at our planet. Current observations of Eta Carinae suggest that the axis of rotation, which is thought to align with the direction of any future jets, is not aimed at Earth. Instead, the beams would likely be angled away into the galaxy, sparing us from a direct hit. But even if we are not directly in the line of fire, a hypernova-generated GRB from Eta Carinae would still be a monumental event. At 7,500 light-years away, its gamma radiation could affect the upper layers of our atmosphere, possibly leading to detectable chemical changes, such as increased nitrogen oxides, which might linger for years. These wouldn't be catastrophic on the level of mass extinction, but they would leave clear fingerprints in the atmosphere, reminders that a distant star's death can still touch us across vast interstellar gulfs. To grasp the scale of the risk, imagine the destructive reach of a GRB compared to a supernova. A typical supernova can cause trouble for planets within about 30 light-years, mostly through radiation and shockwaves. But a gamma-ray burst is far more focused and can be dangerous over thousands of light-years. That Eta Carinae is within this range is what makes the idea so unnerving. Even though the odds of Earth being in the line of fire are slim, the potential severity keeps astronomers vigilant. Interestingly, the possibility of a GRB from Eta Carinae also excites scientists because it would give humanity a front-row seat to one of the rarest phenomena in astrophysics. Gamma-ray bursts are usually observed in galaxies billions of light-years away, appearing as faint, fleeting flashes of radiation on detectors. To have one occur in our own galaxy would provide an unprecedented chance to study the phenomenon in detail. We could probe how the jets form, how they interact with surrounding matter, and how they shape the aftermath of stellar collapse. For astrophysics, it would be a once-in-a-civilization event, even if it carried risks. The thought of a gamma-ray burst from Eta Carinae is both terrifying and awe-inspiring. It reminds us of how fragile life is in the face of cosmic violence. Our planet's survival depends not only on local conditions but also on forces light-years away, playing out on scales almost beyond comprehension. Eta Carinae, with its immense power and instability, sits as a reminder that the universe is both nurturing and hostile, capable of birthing life and extinguishing it with equal ease. For now, the consensus among astronomers is that Earth is likely safe. The beams, if they form, should point away from us. Still, the mere fact that we can calculate such possibilities shows how closely we watch this star and how deeply it fascinates us. It is not just a star, it is a cosmic gun barrel, loaded and waiting, with humanity watching from the sidelines, hoping it is not pointed in our direction. For all the awe and trepidation that Eta Carinae inspires, It's important to pause and remember this: Earth is safe. As dangerous as this massive star may seem, as unstable and volatile as it is, the sheer distance between us and Eta Carinae acts as a cosmic shield. Located roughly 7,500 light-years away in the Carina constellation, it is far beyond the threshold at which its explosion, whether supernova or hypernova, could pose a direct threat to our planet's survival. To put this into perspective, scientists generally consider a supernova dangerous to Earth if it occurs within about 30 to 50 light-years. At those ranges, the radiation, shockwaves, and cosmic rays could disrupt Earth's atmosphere, damage the ozone layer, and trigger harmful effects on life. At 7,500 light-years, Eta Carinae is more than 150 times farther away than the danger zone. Even if it were to unleash the most violent hypernova imaginable, the energy would spread outward in all directions, diminishing over distance. By the time it reached Earth, it would be diluted to the point where its effects would be dramatic in the sky but not catastrophic to life. This is why astronomers confidently say that while Eta Carinae is a star worth watching closely, it is not a star worth fearing. It is not a cosmic executioner waiting to snuff out Earth. Instead, it is a celestial performance, one we are fortunate enough to witness from the safety of a distant balcony. Even the much-feared gamma-ray burst scenario, while theoretically alarming, poses little real danger to us. As I explained earlier, the jets of energy released during such an event are narrow and directional, like twin laser beams. For Earth to be harmed, we would need to be directly in line with one of those beams. The overwhelming consensus from observations is that Eta Carinae's rotational axis, and thus the likely direction of any future gamma-ray jets, is not aligned with Earth. In all probability, those beams will shoot harmlessly into other regions of the galaxy, missing us entirely. That said, the explosion will still be visible in breathtaking fashion. When Eta Carinae finally dies, it will almost certainly become a spectacle unlike anything modern humanity has ever seen. The light alone could rival or even surpass the brightness of the full moon, visible in the daytime sky and illuminating nights for weeks or months. It may cast shadows, disrupt nocturnal animal behavior, and inspire awe around the globe. But what it will not do is threaten Earth's ecosystems or humanity's survival. This assurance allows scientists and the public alike to focus on the scientific opportunities and aesthetic wonder the event will bring, rather than on fear. Imagine living in a time when the night sky itself transforms for months, when the death of a distant star becomes a global event shared by every human being under the same heavens. That will be Eta Carinae's gift to Earth, not destruction, but wonder, inspiration, and discovery. In fact, the distance works out perfectly for us. Too close, and Eta Carinae's fury would be catastrophic. Too far, and its eventual explosion would be just another faint pinprick of light lost in the cosmos. At 7,500 light-years, it sits in a cosmic sweet spot, far enough to spare us danger, but close enough to dazzle us and revolutionize astronomy when it finally goes off. For now, Eta Carinae is a celestial ticking clock. It is a reminder of the violence and beauty of the universe, a warning that not all stars live peacefully, and a promise that even across unfathomable distances, the cosmos can still touch us, not with harm, but with wonder. When its end comes, Earth will be safe, and humanity will have front-row seats to one of the greatest spectacles the galaxy has to offer. Even though Eta Carinae is far enough away that its deadly effects would not reach Earth, its final explosion would still transform our skies in a way no one alive today has ever witnessed. If the star were to go supernova, or even hypernova, the resulting brilliance would be nothing short of astronomical theater, a light show visible across the globe, even in broad daylight. This is the paradoxical beauty of Eta Carinae, lethal in theory, yet spectacular in reality, a cosmic spectacle safely staged 7,500 light-years away. To understand just how astonishingly bright it would be, consider the historical precedent of supernovae visible from Earth. The famous SN 1054, which created the Crab Nebula, was bright enough to be seen during the day for weeks. Eta Carinae's eventual explosion is expected to be at least as bright, and likely much brighter, due to its enormous mass and energy potential. Scientists estimate that at peak brightness, the supernova could outshine the moon, casting its ethereal glow across the night sky and possibly even making daylight skies noticeably brighter in its vicinity. Unlike typical stars, which are mere points of light even through telescopes, Eta Carinae's death would dominate the sky. The star's light would be hundreds of thousands to millions of times brighter than the Sun in visible wavelengths from Earth's perspective, not literally rivaling the Sun's brilliance in total energy, but enough to create a vivid, unmistakable presence that would astonish anyone looking up. This is because brightness diminishes with distance, but Eta Carinae's immense intrinsic luminosity ensures that even across thousands of light-years, it would still be a dominating feature of the sky. Observers on Earth could see this spectacle even without telescopes or binoculars. In the months following the explosion, the star could cast shadows, illuminate the landscape at night, and create a surreal sense of a second sun in the sky. Ancient humans who witnessed similar events often recorded them as omens, signs, or divine phenomena, and modern viewers would likely experience a similar sense of awe and wonder, albeit with a scientific understanding of what was happening. The spectacle would also evolve over time. Initially, the supernova's light would surge rapidly, dominating the sky, but as weeks and months pass, it would gradually fade. This fading would be accompanied by changes in color and intensity. The explosion would start with brilliant bluish-white light due to extremely hot gases, then slowly shift to warmer tones as the ejected material expanded and cooled. For astronomers, this light curve is a goldmine, offering clues about the explosion's energy, the star's composition, and the dynamics of its outer layers. Even daylight visibility is within the realm of possibility, although not to the point of blinding us like the Sun. In the days immediately after the explosion, the star might be faintly perceptible in the daytime sky, especially if viewed from a shaded area or with proper protective equipment. At night, however, it would be impossibly bright, visible across the globe in both hemispheres where the Carina constellation is above the horizon. The Homunculus Nebula, remnants of the Great Eruption, would interact with this newfound brilliance, reflecting and scattering light in intricate ways. The surrounding gas and dust would illuminate, producing a halo or glowing cloud around the star's location, adding layers of spectacle to the already mind-boggling display. For astrophotographers and professional observatories, the opportunity to capture such images would be unparalleled, revealing details of the explosion and its interaction with the surrounding material in ways we could only dream of until now. In essence, Eta Carinae's explosion would be a cosmic fireworks display unlike anything humanity has ever witnessed. It would outshine almost every other celestial object in the sky, become the focal point of global attention, and offer a rare chance to witness the death of one of the universe's most extreme stars in real time. This visibility, combined with the knowledge that the Earth itself would be safe, makes Eta Carinae's eventual supernova or hypernova not only a scientific treasure but a once-in-a-lifetime spectacle of natural wonder. Eta Carinae's eventual explosion represents not only a cosmic spectacle for the naked eye, but also a once-in-a-lifetime opportunity for astronomers to study the death of a supergiant star in unprecedented detail. Supernovae are inherently rare and, for the most part, occur in distant galaxies, often millions or even billions of light-years away. These distances make detailed observation difficult, limiting our ability to study the intricate physics of the explosion, the structure of the progenitor star, and the behavior of ejected material. Eta Carinae, at a relatively close 7,500 light-years, would be the nearest extreme supernova humanity has ever had the chance to observe, allowing scientists to investigate stellar death at a level of detail impossible elsewhere. One of the primary areas of impact would be in understanding the mechanics of supernova explosions. Despite decades of theoretical work, astrophysicists still grapple with the precise processes that govern how massive stars collapse. A nearby explosion would enable high-resolution spectroscopy, photometry, and imaging across the electromagnetic spectrum, X-rays, ultraviolet, visible light, infrared, and radio waves. Observatories could track the evolution of the shockwave in real time, measure the velocities and composition of the ejected material, and directly observe how the star's outer layers are stripped away during the detonation. Eta Carinae's proximity would also allow scientists to study pre-supernova conditions in extraordinary detail. Thanks to decades of monitoring, astronomers already have a wealth of data on its brightness, erratic eruptions, wind collisions, and surrounding nebula. When the star finally explodes, they will be able to correlate these pre-explosion observations with the supernova itself. This could provide the clearest understanding yet of how massive stars transition from unstable giants to explosive endpoints, helping solve long-standing puzzles about mass loss, stellar instability, and eruption precursors. Another critical area of study would be the interaction with circumstellar material, particularly the Homunculus Nebula. As the explosion's shockwave collides with the gas and dust ejected in previous eruptions, it will produce brilliant X-ray and radio emissions. Observing this interaction will give astronomers a rare laboratory to study how stellar explosions propagate through complex environments, including feedback mechanisms that can influence nearby star formation. Essentially, the death of Eta Carinae will not only illuminate the star itself but also shed light on how massive stellar deaths reshape their galactic neighborhoods. A nearby supernova would also provide opportunities to investigate the nucleosynthesis of heavy elements. Supergiant stars like Eta Carinae are factories for creating elements heavier than hydrogen and helium through nuclear fusion. When they explode, they scatter these elements into the interstellar medium, seeding the galaxy with the building blocks for planets, life, and future stars. Observing Eta Carinae's explosion would let scientists directly measure which elements are produced, in what quantities, and how they are distributed, offering invaluable insight into the chemical evolution of the Milky Way. The proximity also allows unprecedented temporal resolution. Most supernovae are detected after their peak brightness or only gradually observed over days to weeks. Eta Carinae, by contrast, will be visible immediately, and astronomers can study its initial explosion in real time, capturing the very first moments of the core collapse. This initial phase is critical for testing theoretical models of stellar death, including energy release, neutrino production, and shockwave propagation, phenomena that are usually inferred indirectly from distant, incomplete data. Finally, a nearby supernova would spur technological and observational advances. Telescopes on Earth and in space would be repurposed and calibrated to capture every aspect of the event. Instruments capable of measuring X-rays, gamma rays, and even gravitational waves could provide complementary data, offering a holistic view of a massive star's final moments. Essentially, Eta Carinae would act as a live classroom for astrophysics, allowing scientists to test theories and refine models that have, until now, relied largely on simulations and distant observations. In summary, the death of Eta Carinae would revolutionize astronomy. It would allow direct observation of the processes that govern the life cycles of the universe's most massive stars, provide insight into the creation and distribution of heavy elements, and illuminate the complex dynamics of supernova explosions and their interactions with surrounding material. For scientists, it would be the equivalent of opening a cosmic laboratory window that has never been so close before, a rare chance to witness, measure, and understand one of the universe's most violent and transformative phenomena in real time. Even before Eta Carinae reaches the catastrophic climax of a supernova or hypernova, it is already an extraordinary source of high-energy phenomena, particularly in the form of X-rays and other radiation. Scientists have long been fascinated by the intense radiation produced by the star system, largely because of the interaction between the stellar winds of its two massive stars. These winds are among the fastest and most violent in the known universe, reaching speeds of thousands of kilometers per second, and when they collide, they create conditions so extreme that the energy released is detectable across vast distances. X-ray telescopes, both in orbit and on Earth, have been instrumental in revealing the hidden dynamics of Eta Carinae. Observatories like Chandra X-ray Observatory and XMM Newton have captured detailed images and spectra showing the wind collision zone, where the winds of the primary and companion stars slam into each other at supersonic speeds. These collisions heat the gas to tens of millions of degrees Kelvin, producing X-rays of extraordinary intensity. By studying these X-rays, scientists can measure the temperature, density, and velocity of the gas in real time, providing a unique window into processes that would otherwise be impossible to study. The variability of X-ray emissions is one of the most revealing aspects of Eta Carinae's behavior. As the two stars orbit each other in their highly elliptical 5.5-year cycle, the intensity of the X-ray emissions fluctuates dramatically. During periastron, the point at which the stars are closest, X-ray output spikes due to the increased interaction of the stellar winds, then drops as the stars move apart. Monitoring these changes has allowed astronomers to map the geometry of the system, understand the strength and structure of the winds, and even refine estimates of the star's masses and orbital characteristics. X-ray studies also provide critical insights into shock physics. When the supersonic winds collide, they form shock fronts that accelerate particles to extremely high energies, producing not just X-rays but also gamma rays. These shocks are natural laboratories for studying phenomena that occur in more extreme environments, such as supernova remnants and the jets of active galactic nuclei. Eta Carinae's proximity makes it the perfect nearby example to study these processes in exquisite detail, something that is often impossible with more distant or less energetic systems. Beyond X-rays, Eta Carinae also emits ultraviolet and radio waves as a result of its energetic outflows. These emissions help scientists build a more complete picture of the star's environment, including how the radiation interacts with the Homunculus Nebula. By combining data across the electromagnetic spectrum, researchers can trace the flow of energy from the core of the system outward, linking the violent stellar winds to the broader dynamics of the nebula and interstellar space. Another key application of X-ray and radiation studies is predicting potential eruptions or precursors to a supernova. Sudden spikes in high-energy emissions can signal changes in the stability of the star's outer layers or indicate that mass ejections are underway. By carefully monitoring Eta Carinae, astronomers hope to identify warning signs that might precede its ultimate collapse, allowing humanity to observe one of the universe's most extreme explosions in unprecedented detail. In essence, Eta Carinae is not just a ticking time bomb waiting to explode. It is also a natural laboratory of high-energy astrophysics. Its colliding winds, X-ray emissions, and complex radiation environment provide a wealth of information about the behavior of massive stars under extreme conditions. Every spike, dip, and fluctuation in X-rays brings scientists closer to understanding how massive stars live, interact, and ultimately die, offering a rare glimpse into cosmic processes that shape galaxies. The Homunculus Nebula is one of the most striking and scientifically valuable features of the Eta Carinae system, serving as both a monument to its past violence and a laboratory for studying the physics of massive stars. Formed during the Great Eruption of the 1840s, the nebula is a massive bipolar cloud of gas and dust ejected from the star, now stretching roughly 7 trillion kilometers across. Its unique shape, composition, and structure provide astronomers with an extraordinary record of the eruption, enabling them to analyze how such colossal outbursts unfold and how stars lose mass in extreme circumstances. One of the most important insights the homunculus provides is the mechanism of stellar mass loss in supermassive stars. Massive stars like Eta Carinae cannot hold onto all their mass indefinitely. Radiation pressure, turbulence, and instabilities in their outer layers eventually push gas and dust away into space. The homunculus represents a snapshot of this process in action. By measuring the mass of the nebula, estimated at 10 to 20 solar masses, astronomers gain direct information about how much material Eta Carinae ejected during the Great Eruption. This, in turn, helps refine models of how massive stars evolve and sheds light on the extreme conditions leading up to their ultimate demise. The bipolar shape of the homunculus is another key feature for scientific study. Unlike a simple spherical shell, the nebula forms two distinct lobes extending in opposite directions from the central star. This structure suggests that the mass ejection was highly directional, influenced by the star's rotation, magnetic fields, and the gravitational effects of its companion. By analyzing the geometry of the nebula, astronomers can infer the physical forces at work during the eruption, gaining clues about how such violent events are channeled into specific directions rather than being uniformly explosive. Spectroscopy of the homunculus has revealed detailed chemical fingerprints of the ejected material. The gas is enriched with elements such as nitrogen and helium, indicating that it originates from layers deep within the star that have undergone nuclear processing. Studying these chemical abundances allows scientists to see the inner workings of the star long before it goes supernova. Essentially, the nebula acts as a fossilized record of the star's internal processes, showing what material has been dredged up from the core and expelled into space. The homunculus also provides a window into the dynamics of stellar eruptions over time. Observations show that the lobes are expanding at speeds of several hundred kilometers per second, slowly dispersing into the surrounding interstellar medium. By tracking the motion and evolution of the nebula, astronomers can reconstruct the timeline of the Great Eruption and understand how energy is distributed during such an event. This kind of analysis is nearly impossible for stars in other galaxies because their ejected material is often too distant and faint to study in detail. Eta Carinae, however, gives us a close-up laboratory for extreme stellar phenomena. Additionally, the homunculus interacts with the intense radiation and winds from the central stars, producing shock fronts, high-energy emissions, and intricate light scattering patterns. These interactions allow scientists to study how expelled material behaves in a harsh stellar environment, providing insights applicable to other massive star systems and supernova remnants. By understanding these processes, researchers can better predict how massive stars contribute to the chemical enrichment of galaxies and influence future star formation. In short, the Homunculus Nebula is far more than a beautiful structure in space. It is a living archive of Eta Carinae's past, an active laboratory for studying the physics of massive stars, and a predictive tool for what might happen when the star finally explodes. Its shape, motion, and composition tell a story of enormous energy, violent instability, and mass ejection on a scale almost impossible to imagine. For astronomers, it is a rare gift, a chance to study the life cycle of one of the universe's most extreme stars, both before and after its violent eruptions. The Great Eruption of Eta Carinae, which occurred between roughly 1837 and 1858, was one of the most extraordinary stellar events ever recorded, and it captured the attention of astronomers around the world. At the time, the star suddenly became the second brightest object in the night sky, rivaled only by Sirius, and for a period even outshone all stars in the southern hemisphere. Observers of the era, armed with telescopes that were primitive by today's standards, meticulously documented its rise and fall, creating a wealth of historical data that continues to inform modern astronomy. Early observations began with the Chilean and European astronomers who monitored southern skies. One of the first to notice the unusual brightening was John Herschel, a prominent astronomer based in the Cape of Good Hope. He recorded the star's increasing luminosity and noted its erratic changes over time. Herschel and others were struck by its sudden brilliance and by the fact that it appeared to fluctuate in intensity, sometimes brightening dramatically within months and then dimming unexpectedly. The star's behavior defied the expectations of the day, challenging the prevailing understanding of stellar stability. The Great Eruption was so dramatic that it shocked the astronomical community, raising fundamental questions about the nature of stars. In the early 19th century, theories of stellar physics were rudimentary. Stars were thought to be largely unchanging, eternal points of light, and the idea that a star could undergo such a violent, extended outburst was almost inconceivable. Observers struggled to reconcile the appearance of a star that could briefly rival Venus in brightness while remaining hundreds of times more distant than any nearby planet. Contemporary records show that the star's light was clearly visible to the naked eye, casting faint shadows at night in the southern hemisphere. Accounts from explorers, sailors, and early astronomers described the eerie beauty of the star, with its intense glow dominating the night sky. Many of these observations were later compiled and analyzed, forming a continuous record of the eruption that has allowed modern astronomers to reconstruct the timeline, intensity, and effects of the event with remarkable accuracy. The eruption also prompted speculation and debate about its cause. Some observers wondered whether Eta Carinae had truly exploded and then somehow survived, while others questioned whether a new star had suddenly appeared. The distinction between a supernova and this extraordinary but non-terminal eruption was not understood at the time. Without the theoretical framework of stellar evolution, astronomers could only record what they saw and attempt to interpret it with limited knowledge. Perhaps most remarkable is that the Great Eruption lasted over 2 decades, unlike typical supernovae, which flare and fade over weeks or months. This extended duration gave astronomers a unique opportunity to monitor the star systematically, tracking the peaks, plateaus, and declines in brightness. Their careful notes and sketches created a historical archive that modern researchers still rely on to model Eta Carinae's behavior and predict its future evolution. The eruption also left a lasting physical legacy in the form of the Homunculus Nebula, which would not be directly observed until much later but is now understood as a direct result of this violent episode. Early astronomers had no way of knowing that the massive lobes of gas and dust surrounding Eta Carinae were the remnants of its 19th century convulsion. However, their meticulous documentation of the star's brightness, combined with later observations, allowed astronomers to connect the nebula with the eruption, giving us a detailed view of the cause and effect relationship between extreme stellar activity and circumstellar structures. In essence, the Great Eruption of Eta Carinae was both a scientific shock and a catalyst for discovery. It demonstrated that stars could be dynamic and unpredictable, that massive eruptions could occur without immediate death, and that stellar behavior was far more complex than previously imagined. The historical records provide a bridge between the 19th century observations and modern astrophysical analysis, allowing scientists to study the long-term consequences of such events, including mass loss, nebula formation, and the approach to a final supernova or hypernova. The careful observations of 19th century astronomers remind us that even before modern telescopes, humanity could witness extraordinary cosmic phenomena and attempt to make sense of them. Their work laid the foundation for the detailed, high-energy astrophysics we conduct today and serves as a testament to the enduring human curiosity about the cosmos. Without their records, the story of Eta Carinae's Great Eruption would be far less complete, and our understanding of massive star evolution would be correspondingly poorer. The advent of modern astronomical technology, particularly space-based observatories like the Hubble Space Telescope, has revolutionized our understanding of Eta Carinae, allowing scientists to observe the star and its surrounding nebula with unprecedented clarity and detail. Whereas 19th-century astronomers could only track its brightness and sketch rudimentary impressions, Hubble and other instruments have peeled back layers of obscurity, revealing the star's complex structure, its violent environment, and the intricate morphology of the Homunculus Nebula. One of the most striking revelations from Hubble has been the bipolar shape and fine structure of the Homunculus Nebula. High-resolution imaging shows that the nebula is not simply a pair of smooth lobes but is composed of filaments, clumps, and intricate patterns of gas and dust, tracing the paths of past eruptions and mass ejections. These details provide astronomers with crucial insights into how Eta Carinae expelled material during the Great Eruption and how forces such as stellar rotation, magnetic fields, and the companion star's gravity influence the directionality of the outflows. In many ways, the nebula serves as a three-dimensional map of the star's violent past. Space-based instruments also allow observations across different wavelengths, from ultraviolet to infrared to X-rays, each revealing unique aspects of the star and its environment. For example, Hubble's ultraviolet and visible light cameras can penetrate some of the outer dust, showing the luminous central stars and the reflective surfaces of the nebula. Infrared observations, including those from the Spitzer Space Telescope, detect cooler dust structures hidden from visible light telescopes, giving a more complete picture of how the ejected material has spread and cooled over time. Meanwhile, X-ray observatories like Chandra reveal the energetic collisions of stellar winds, highlighting areas of intense shock heating and particle acceleration. Combining these datasets produces a multi-layered, multidimensional portrait of Eta Carinae that was unimaginable just decades ago. Hubble has also captured changes in the nebula over time, allowing astronomers to measure expansion rates with incredible precision. By comparing images taken years apart, scientists can calculate how fast the lobes of the homunculus are moving, several hundred kilometers per second, and trace the eruption's energy output. This ability to measure movement in real time provides critical data for understanding the dynamics of massive star eruptions, the forces shaping circumstellar nebulae, and the long-term evolution of the system as it marches toward its ultimate demise. Another profound contribution of modern technology is the direct study of Eta Carinae's binary system. Hubble, along with ground-based adaptive optic systems, has resolved the two massive stars in the system, allowing astronomers to monitor their orbital dance, interactions, and the periodic variations in brightness and radiation. Observing the wind collision zone and the resulting X-ray emission in conjunction with optical and infrared imagery provides a holistic understanding of how these two enormous stars influence each other, fueling instability and shaping the surrounding nebula. Modern spectroscopy, enabled by instruments aboard Hubble and other space telescopes, has unlocked the chemical composition of the nebula and stellar winds. By analyzing the light emitted at different wavelengths, astronomers can detect the presence of elements like nitrogen, helium, and carbon, as well as heavier metals forged in the star's core. This gives unparalleled insight into the internal workings of a supermassive star and helps scientists trace how these elements are distributed into the interstellar medium during eruptions, a process critical for understanding galactic chemical evolution. Perhaps most dramatically, Hubble has captured the sheer scale and majesty of Eta Carinae in images that look almost sculptural. The nebula's lobes, the clumps of gas and dust, and the brilliant light from the central stars combine to create an awe-inspiring visual that conveys both the power and fragility of the system. These images have not only advanced scientific knowledge but have also inspired generations of astronomers and the public alike, demonstrating the beauty of the universe's extremes. In short, modern technology has transformed Eta Carinae from a mysterious, flickering point of light into a well-characterized, dynamic system. Observations from Hubble and other telescopes have revealed its complex structure, illuminated its violent history, and provided predictive insight into its future. Every detail captured, from the filaments of the homunculus to the interactions of the stellar winds, brings scientists closer to answering some of the universe's most profound questions about the life cycles of supermassive stars. Eta Carinae is more than just a fascinating star. It is a symbol of stellar extremes, representing the outer limits of what stars in our universe can achieve in terms of mass, luminosity, and instability. Most stars, including our Sun, live relatively calm lives, burning hydrogen steadily for billions of years and evolving in predictable ways. Eta Carinae, however, lives at the edge of physical possibility, challenging our understanding of stellar evolution and demonstrating just how violent, massive, and unpredictable stars can become. One of the defining features of Eta Carinae's extremity is its sheer mass. The primary star alone is estimated to be between 100 and 150 times the mass of the Sun, while its companion adds another 30 to 80 solar masses. Stars of this magnitude are exceedingly rare, as the forces of radiation and gravity conspire to make it difficult for such massive stars to form or survive for long periods. In comparison, the Sun is relatively small and stable, and even other famous giants like Betelgeuse are significantly less massive than Eta Carinae. Its enormous mass allows it to generate astronomical luminosity, outshining the Sun by millions of times, and to sustain violent internal pressures that push it toward instability. This extreme mass and luminosity directly contribute to the star's unstable behavior. Unlike smaller stars, which maintain equilibrium for billions of years, Eta Carinae experiences tremendous radiation pressure from its core. This pressure drives violent stellar winds and periodic eruptions, including the historic Great Eruption in the 1840s. Its variability, massive mass loss, and propensity for unpredictable outbursts illustrate the precarious balance at the high end of the stellar mass spectrum. In essence, Eta Carinae is a living example of how stars behave when pushed to their physical limits. Eta Carinae also embodies extremes in terms of energy output and violent interactions. The binary systems colliding stellar winds produce shockwaves that emit intense X-rays and gamma rays, making it one of the most energetic star systems in our galaxy. Its eruptions eject enormous amounts of material at high velocities, sculpting intricate nebulae and dispersing elements across space. These phenomena showcase processes that are almost inconceivable in smaller, more stable stars, underscoring the unique position of Eta Carinae as a laboratory for studying the universe's most violent stellar behaviors. Moreover, Eta Carinae is extreme not only physically but temporally. Massive stars burn through their fuel incredibly quickly compared to smaller stars. While the Sun's expected lifetime is roughly 10 billion years, Eta Carinae's few million years of existence place it in a category of stars that live fast and die young. Its current stage, marked by instability, mass ejections, and high luminosity, demonstrates the fleeting but spectacular life of hypergiant stars, a type of stellar extreme that is both rare and scientifically invaluable. Finally, Eta Carinae is extreme in its potential for cosmic impact. Its eventual death as a supernova or hypernova will release energies far exceeding that of typical stellar explosions, producing heavy elements essential for forming planets, and potentially generating gamma-ray bursts if conditions align. It shows how a single star, by virtue of its extraordinary size and energy, can shape its surrounding interstellar environment and leave a lasting legacy on the galaxy. In sum, Eta Carinae stands as a paragon of stellar extremes. Its mass, luminosity, violent eruptions, rapid evolution, and cosmic influence all push the boundaries of what stars are capable of. Observing and studying this star allows astronomers to explore the limits of stellar physics, offering insights into phenomena that smaller, less extreme stars can never reveal. Eta Carinae is not just a star, it is a cosmic benchmark, a reminder of the staggering scale and power that nature can achieve when it creates a stellar giant on the edge of possibility. Eta Carinae is not merely an extraordinary star because of its mass or luminosity. It is also one of the most unstable giants in the Milky Way, living on borrowed time as a ticking cosmic time bomb. Its very existence teeters on the edge of physical possibility, and every observation we make underscores the delicate balance between its immense gravitational pull and the enormous outward pressure of radiation from its core. Unlike stable stars such as our Sun, which can shine steadily for billions of years, Eta Carinae exists in a state of almost constant flux, with eruptions, violent winds, and structural instabilities marking its short, volatile life. The instability of Eta Carinae is driven primarily by its immense mass and luminosity. Stars of this size generate enormous radiation pressure in their cores, which pushes outward with tremendous force. At the same time, gravity pulls inward, striving to hold the star together. In smaller stars, This balance is relatively stable, but in a hypergiant like Eta Carinae, the forces are so extreme that equilibrium is tenuous at best. Minor fluctuations in the core can trigger massive eruptions or bursts of energy, as evidenced by the historic Great Eruption of the 1840s, when the star expelled tens of solar masses of material in a relatively short period. Eta Carinae's binary nature compounds this instability. The gravitational interaction between the primary star and its massive companion creates tidal forces that distort their shapes and stir the stellar interiors. These interactions influence the timing and intensity of eruptions, drive the violent colliding winds, and contribute to fluctuations in brightness. The system's 5.5-year orbital period results in periodic surges in activity, particularly near periastron when the stars come closest together, producing bursts of X-rays and altering the dynamics of the surrounding nebula. Even outside these predictable orbital interactions, Eta Carinae exhibits erratic, unpredictable behavior. Its brightness continues to fluctuate, sometimes on short timescales, defying easy prediction. These fluctuations are not merely cosmetic, they indicate real changes in the star's outer layers, mass loss rates, and internal stability. Each surge of energy, each ejection of material, brings the star incrementally closer to its ultimate demise. From a human perspective, this unpredictability adds to the sense of watching a cosmic ticking clock, where the final explosion could happen at any time, or not for several millennia. The term living on borrowed time is particularly apt because Eta Carinae has already survived events that might have destroyed a less massive star. The Great Eruption released energy equivalent to a supernova but fell short of fully annihilating the star. This resilience shows that Eta Carinae is extraordinarily robust, but it also underscores that it is using up its remaining reserves with each eruption. The star's core is slowly exhausting its nuclear fuel, and as it progresses toward the end of its life, the likelihood of catastrophic collapse grows with every passing century. Astronomers liken Eta Carinae to a ticking time bomb because of its combination of potential energy, instability, and uncertainty. The primary star is so massive that its eventual collapse will almost certainly result in either a supernova or a hypernova, and the exact timing remains unpredictable. Every day that passes, the star edges closer to a violent end, and when it finally occurs, the explosion will be unimaginably energetic, reshaping the surrounding interstellar medium and illuminating the night sky in a dramatic cosmic display. Yet, despite its instability and impending doom, Eta Carinae also represents an unparalleled opportunity for science. Its precarious state provides astronomers with a live case study of the final stages of hypergiant evolution. By monitoring its winds, eruptions, X-ray emissions, and nebular interactions, scientists gain insight into the processes that precede stellar death, refining models for supernovae, hypernovae, and gamma-ray bursts. In a sense, the star's instability is both a threat and a laboratory, allowing humanity to study phenomena that are otherwise exceedingly rare and distant. In summary, Eta Carinae's life is a precarious dance between creation and destruction. It is massive, luminous, and violently unstable, with every eruption and wind-driven convulsion serving as a reminder that its time is finite. Like a cosmic time bomb, it is poised to detonate at some unpredictable moment, offering both a spectacular celestial display and a window into the physics of the universe's most extreme stars. Every observation we make is a countdown closer to an event of unimaginable scale, and humanity is privileged to witness a star living so dangerously close to the edge of cosmic possibility. Eta Carinae occupies a special place in the pantheon of massive stars, standing out even among other famous stellar giants such as Betelgeuse or the many Wolf-Rayet stars scattered across the galaxy. Betelgeuse, the red supergiant in Orion, has captured the public imagination because of its size and relatively close proximity, roughly 700 light-years away. It is enormous, about 1,000 times the Sun's radius, and nearing the end of its life, with the potential to go supernova within the next 100,000 years. However, in comparison to Eta Carinae, Betelgeuse is almost gentle. While Betelgeuse's explosions and variability are notable, its mass is only about 20 solar masses, and it does not exhibit the extreme, sustained eruptions or violent colliding winds characteristic of Eta Carinae. Its death, though spectacular, would pale in intensity and scale relative to the cataclysmic potential of Eta Carinae. Wolf-Rayet stars, on the other hand, are perhaps more similar to Eta Carinae in some respects. They represent a later stage of evolution in massive stars, characterized by intense mass loss and extremely powerful stellar winds, sometimes exceeding several thousand kilometers per second. These stars often appear as brilliant, hot, and highly unstable points of light in the sky, stripped of their hydrogen layers and nearing the ends of their lives. Wolf-Rayet stars are the universe's harbingers of supernovae, and in that sense, they share with Eta Carinae the themes of instability and imminent destruction. However, most Wolf-Rayet stars are solitary or part of less extreme binary systems. They do not combine the mind-boggling mass, binary complexity, and historical eruptions seen in Eta Carinae. The combination of a hypergiant primary and a massive companion, producing periodic collisions of stellar winds and violent outbursts, sets Eta Carinae apart even from these otherwise extraordinary stars. Eta Carinae's uniqueness is also amplified by the scale of its Great Eruption in the 19th century, an event with no true parallel among nearby massive stars. While Betelgeuse has shown modest dimming events, and some Wolf-Rayet stars undergo significant mass loss, Eta Carinae expelled tens of solar masses of material in a single eruption, temporarily becoming the second brightest star in the sky. This kind of outburst, more powerful than many supernovae in terms of total energy release but still allowing the star to survive, is unparalleled in the modern observational record. Its ability to sustain violent eruptions without collapsing immediately demonstrates both its resilience and its position at the very edge of stellar physics. Additionally, Eta Carinae's binary system contributes to its singular nature. While some Wolf-Rayet stars exist in binaries, few display the kind of extreme interactions that Eta Carinae does. The gravitational and radiative interplay between its two massive stars produces complex colliding wind zones, X-ray flares, and irregular luminosity variations, creating a dynamic environment that challenges theoretical models. This makes Eta Carinae not just another massive star but a laboratory for extreme astrophysics, combining mass, energy, instability, and binary dynamics in a way that has few parallels in the Milky Way. In terms of sheer mass, luminosity, and potential for violent cosmic events, Eta Carinae surpasses almost all other known stars. While Betelgeuse and Wolf-Rayet stars are remarkable and teach us much about stellar life cycles, Eta Carinae represents the upper limit of what stars can become, a combination of energy, size, instability, and binary complexity that is unmatched in both the nearby universe and, likely, across our galaxy. Its eruptions, colliding winds, and eventual catastrophic death will dwarf the phenomena associated with other supergiants, making it a singular object of study for astrophysicists and an unparalleled spectacle for humanity. When Eta Carinae finally reaches the end of its life, its explosion, whether as a supernova or a hypernova, will not only be a spectacular display in the night sky, it will also reshape the chemical landscape of its galactic neighborhood, leaving a lasting legacy that extends far beyond its immediate vicinity. Stars like Eta Carinae are cosmic forges, synthesizing heavy elements through nuclear fusion in their cores over millions of years. While lighter elements like hydrogen and helium dominated the early universe, the creation and dissemination of heavier elements, carbon, oxygen, nitrogen, iron, and beyond, depend entirely on the death throes of massive stars. Eta Carinae's imminent explosion will distribute these elements into space, enriching the interstellar medium and providing the raw material for future generations of stars, planets, and even life itself. The process begins in the core of the star, where nuclear fusion produces layers of heavier and heavier elements as the star ages. In its final moments, the pressure and temperature rise to extremes, allowing rapid nucleosynthesis that generates elements heavier than iron, including nickel, cobalt, and other metals. When the star explodes, these materials are ejected at thousands of kilometers per second, spreading across nearby space. The Homunculus Nebula, formed during the Great Eruption, has already begun to enrich its surroundings with nitrogen, helium, and other elements. But the ultimate supernova or hypernova will dramatically amplify this effect, scattering a stellar wind of heavy elements across the galaxy. This cosmic recycling is essential for the formation of planets and, eventually, life. Without the death of massive stars, the universe would remain a place dominated by hydrogen and helium, incapable of producing rocky planets or the complex chemistry necessary for organic molecules. Eta Carinae's eventual explosion will seed regions of space with elements like carbon, oxygen, magnesium, and iron, the very same building blocks that make up Earth, the Sun, and all living organisms. In a sense, when the star dies, it will plant the seeds of future solar systems, linking its violent end to the birth of new worlds. Moreover, The explosion will influence star formation in nearby regions. The shockwave from a supernova compresses clouds of gas and dust, triggering the collapse of these clouds into new stars. Eta Carinae, with its immense energy output, could spark the formation of dozens or even hundreds of new stars over tens of thousands of years. Its death will not be an isolated event but a catalyst for cosmic regeneration, demonstrating the cyclical nature of stellar evolution. Massive stars form, live briefly but energetically, die explosively, and in doing so, provide the ingredients and conditions for new stars to emerge. The distribution of heavy elements also has long-term consequences for the chemical evolution of the galaxy. Eta Carinae's explosion will enrich the Carina constellation region with metals that are rare in primordial gas clouds. Over time, this enriched material can mix with the interstellar medium, influencing the composition of future stellar generations. Stars forming in this region will inherit higher metallicity, which in turn affects planet formation, stellar evolution, and even the likelihood of life-supporting environments. In a very real sense, Eta Carinae's death will write a new chapter in the chemical story of the Milky Way. From a human perspective, the cosmic legacy of Eta Carinae also offers an extraordinary scientific opportunity. By studying the elements ejected and mapping how they propagate through space, astronomers can learn not only about this individual star but also about the broader processes of galactic chemical evolution. Observations of nearby supernova remnants allow scientists to trace the journey of these heavy elements from stellar core to interstellar medium, providing a tangible connection between the violent death of a star and the formation of future celestial structures. In summary, Eta Carinae's legacy will be one of creation through destruction. Its explosive death will scatter heavy elements across space, enriching the interstellar medium, seeding new stars and planets, and laying the foundations for life itself. While the star is a ticking time bomb in the present, its ultimate contribution to the cosmos is profoundly constructive. The elements it produces will endure long after the light of the explosion fades, perpetuating the cycle of stellar birth, death, and renewal that governs the evolution of galaxies. Eta Carinae, in all its extraordinary complexity, stands as a monument to both the power and unpredictability of the cosmos. From its massive, unstable core to its violent stellar winds, from the titanic Homunculus Nebula to its potential hypernova death, every aspect of this star is a reminder that the universe is far more dynamic and extreme than our daily lives might suggest. As we gaze upon the Carina constellation, we are looking not merely at a point of light but at a cosmic time bomb, a system teetering on the edge of cataclysm, whose final act could illuminate the skies in a display of unimaginable power. The truth about Eta Carinae is as humbling as it is awe-inspiring. It could explode tomorrow, producing a spectacle that would outshine the moon and fill telescopes with streams of data that will reshape our understanding of stellar physics. Or it could remain relatively quiet for thousands of years, continuing to emit its erratic flares, shedding mass, and slowly marching toward an inevitable end. The uncertainty of its timeline reminds us that the universe operates on scales and rhythms far beyond human comprehension. What seems stable in our lifetimes may be precarious on cosmic scales, and what seems distant may nonetheless influence the chemical and energetic makeup of entire regions of space. As observers, humanity occupies a unique position. We have the technology to monitor Eta Carinae in real time, to capture X-rays, gamma rays, infrared light, and visible photons. We can model its wind collisions, measure its mass loss, and map the intricate details of the Homunculus Nebula. Every eruption, every fluctuation in brightness, every shift in X-ray emission is data that brings us closer to understanding one of the universe's most extreme phenomena. We are witnesses to a slow, unfolding drama that has been millions of years in the making, and while we cannot alter the outcome, we can appreciate the magnitude and significance of the events as they unfold. Eta Carinae also serves as a symbol of cosmic perspective. It reminds us that stars, even more massive than our Sun by over 100-fold, are not eternal. They live fast, they shine brilliantly, and they die violently, contributing to the ongoing cycle of creation and destruction that shapes galaxies. Its eventual explosion will seed future stars, planets, and perhaps even life, demonstrating that even catastrophic ends can have constructive, long-lasting effects. Observing Eta Carinae is not just an exercise in science, it is an encounter with the sublime, a reminder of the immense energies and delicate balances that govern the universe. There is also a profound philosophical dimension to Eta Carinae's story. The star's uncertainty mirrors the uncertainty inherent in the universe itself. It exists as a cosmic reminder that life and death, creation and destruction, stability and chaos coexist on unimaginable scales. Every time astronomers track its unpredictable brightness or chart the flow of its colliding winds, we are witnessing the delicate interplay between forces that are both terrifying and beautiful. Eta Carinae is, in a sense, a mirror of the universe's extremes. Massive, volatile, and magnificent, a spectacle that is at once scientific and profoundly poetic. For humanity, there is an extraordinary privilege in simply being present to observe such a system. Unlike the countless stars whose lives and deaths pass unnoticed across the galaxy, Eta Carinae is close enough, bright enough, and violent enough that we can study it intimately. We can anticipate, model, and marvel at its behavior, knowing that when the final explosion occurs, it will be recorded and analyzed in ways that previous generations could never have imagined. And even if that event happens thousands of years from now, every eruption and every flare in the meantime adds pieces to the cosmic puzzle, giving us a glimpse into forces that are otherwise beyond comprehension. Ultimately, Eta Carinae is a cosmic ticking clock, a star that embodies both the extremes of stellar physics and the mysteries of the universe. Its potential death is a reminder of the immense scales of energy, time, and matter that exist beyond our everyday experience. As we watch and study it, we are participants in a story that began millions of years ago, a story that will culminate in a cataclysmic event whose echoes will resonate across the galaxy. Whether it explodes tomorrow or in millennia, humanity has the rare privilege of observing one of the universe's most extreme and compelling phenomena. A star that is simultaneously a ticking time bomb, a creator of cosmic elements, and a testament to the boundless power of the cosmos. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.